Okay, so yeah. So as I can see, till now, 74 of the participants have been joined, and let's wait for another 2-3 minutes. People are joining slowly. So yeah. So today in the first session, we will go through the demonstration part, and in the second session, there will be theory part, and that will be handled by Dr. Sriparna from IIT Patna. So let's wait for another 2-3 minutes. After that, I will start this demonstration part. So in demonstration today, I will show you text classification using CNN. Okay. So CNN, I think you know, it is a deep learning model. So we'll go through that. Okay, so in the chat box, I can see somebody had asked that, sir, can we get the marks of yesterday's quiz? So usually in this kind of programs, we don't disclose the marks. Actually, there is nothing to give you grades, right? Here, only thing is that you are going to pass or not, that matters. So, the 60%, I think 60% is the passing marks. And as I have seen, almost I can say 80% of the people have scored 60%, and many of you have not scored 60%. So that is not something to worry, because we'll have another 2 quizzes, and we are going to consider the best 2 out of 3. Okay, best 2 quizzes out of 3. So even if you have not done good in the previous quiz, yesterday's quiz, or if somebody have missed, so there is nothing to worry. So in the coming 2 quizzes, you should attend, and you should try to answer them, and take time. So there is no hurry to submit your quiz. Take time and see what you are answering. The questions are quite common in the field. So there is, I don't think there is very hard questions that who are new to the field will not be answered. It is not like that. Okay. So our motto is not testing you on a frying pan that you are having very core knowledge or not. Not never. We don't have that intention. Only thing is that if you are attending the session, you will be able to score 60%. Okay, that's all. Okay. Give me 1 minute. Okay, so I think we have given enough time to join people. Okay, and let's start. Let me share my screen.
Sir, I have a question.
Yeah. Go.
Suppose anyone was not able to join the yesterday's session due to some unavoidable reason. So one quiz was there in which was necessary to attempt. So what is the alternate to that?
And that is what I was telling you, that we are going to consider best 2 out of 3 quizzes. Okay. So there will be total 3 quizzes. We will consider best 2 out of them. So everybody's target should be attend at least 2 quizzes and score 60% minimum in these 2 quizzes. Okay. So if you have already missed one, so you have 2 options, 2 quizzes in your hand. You have to attend both of them without missing. Clear?
I think, sir, there should be an option to re-attempt the missed quiz.
No, we will not give that option. That is the reason we are doing 3 quizzes. All right.
Okay, sir. But in the
By the
NLP,
way, we will discuss about your suggestion.
okay, sir. In the schedule, 2 quizzes have been mentioned. So when will this third quiz?
No. There will be 3 quizzes.
Okay,
Okay,
sir. Thank
we will discuss it in the committee again. Okay, because this is a joint program, so we need to discuss with all our other coordinators and other people. Okay, then we will definitely tell you.
Yeah. One question.
Yes.
Yesterday you have shown embedding models. So my question is how
Yeah.
semantic relations are obtained with that embedding model? Relations.
Semantic relations, right?
Yeah.
So what happens? Yesterday, what I have shown, if you see, we have used unigrams, right?
Yes.
We have used unigram. So definitely in unigrams, the semantic relation, and if you think about capture of semantic relation, it will be lesser than the bigram or other hierograms. That is there, but still it captures the it captures the relation. How it captures the relation? If you see, every sentence is converted, converted
Into
to a
tokens.
sequence of
Tokens.
right? And those tokens are converted to a sequence of a vector, right? Tokens are converted to vectors. Now, if you think about this sentence is converted to a vector, so it is a set of vector, right? So which set of vectors happen together, they are having some semantic, or you can say relation. They occurs together, this word usually comes first of that word. So this kind of relation automatically builds. Understand?
Yes, but it will happen with every word with some other word in that vocabulary. Some relation will be there.
Yes,
That you
and
meant to
now
say.
see, after that what happens, I'm telling you, after that what happens, you will see that I have given a diagram also there. It calculates basically similarity between different vectors. Remember, similarity means it calculates distance, and similarity means one minus distance, right? So it is there is a different distance measures are available. So cosine is one of the popular one in this. So cosine distance, it can calculate between two vectors, and it can give you then that similarity.
Okay, so using
Understand?
cosine value between any two words which are occurring, so can be considered as one semantic relation like that.
You can say
Actually,
how they are related, how much. How
Okay.
much they are related finally, it is defined by the cosine distance.
Actually, the aim of asking this question is, suppose I am identifying the two relations, which is say verb. For example, two verbs are similar or not. Usually we use word net, but suppose that that is not available in the word net. So for that, can I use this embedding kind of model, any kind of embedding, which will give me the parallel relation? It means similar to synonym, but it is missing in my word net dictionary.
No. See, there is some fundamental difference between word to vec and word net. What is the difference? Word to vec gives you, you can say, most related words are similar. It says that. Okay, so it does not understand any dictionary meaning. But when you speak about word net, it understands the dictionary meaning. So there is a fundamental difference. Understand?
Okay.
Like in WordNet, you will never find that Alice and Queen are similar word or synonyms, right? It is not possible.
Yes.
Alice is a noun.
Yes.
But
Yes.
when you are doing on word to pay, you will find that there is very high similarity between Alice and Queen. Reason is that in the documents you will find Alice and Queen have been used alternatively.
Okay.
Understand? So
Yes.
basically they are similar thing.
Okay, sir. Thank you.
In the context, here the context is the Nobel, what Nobel we had considered that as a text data. Understand?
Yes.
So
Thank
can I answer this question if it's okay?
I also have a question with the same in the same context. So this means that it is not a semantic similarity. Hello, can you hear me?
Yeah.
Yes, sir.
That is at the beginning. At the beginning I told you that you can't say it is it is semantic similarity, but that similarity depends on what unigram, bigram, or what you are using based on that. Somebody was trying to answer something. Yeah, you can definitely go ahead.
So can I answer to the queries, these queries which were being asked
sure.
for WordNet? Actually, what happens is when you're looking at word to vector or glow or any of the models, these models give you the semantic relatedness between the two words that you are passing, right? They would give you some value.
Yes.
So here you would not get everything on a provided on a platter. Here you have to work with something. You have to come out with a threshold value, and once your similarity value exceeds the threshold value, then you can say that the words are similar or they are synonyms of each other. So that is something which this is the workaround that you can do over there.
But this is not
That
similarity.
is what I said. Yeah? Okay, we can stop this discussion and we can move for today's task. Again, we will discuss in the end. Is that okay?
All right,
Yes.
we can discuss later.
Yes.
Okay. So just a minute. It's coming. Okay, so for today's task, I have taken a data set that is a review data set, a movie review data set. Okay, and it is available on GitHub. Okay, on this link. So I will just pick this from this link and I will use it. Or you can simply download it. I am just pasting this to the chat box. Let me check whether my recording is on or not. Recording is in process. All right. So okay, I posted the link here. You can use that. All right. All right. So what I will do, I will fetch this data from this GitHub website. GitHub. Just a minute. Okay, so before we do, we will import pandas as PD data equal to PD dot read underscore CSV. You give the URL here. Okay, and with this headers are there already, so header equal to none. Let's make it header equal to none. Capital N. Sorry. Header equal to none, and delimiter is here. You can see this is a TSV file. That means the file is tab separated. Okay, so tab is given by /t. Okay, so delimiter equal to /t. Okay. Okay, if I just want to check whether columns are there or not, I think it is not there actually. Oh, sure, let me check. Data dot columns. It is not there. Okay, so it is showing the column index. There is two columns. One column is indexed by 0, another column indexed by 1. So let give name for them. So data dot columns equal to, I provide a list of column name. Say text is first column name, and second column name I give level. Okay. Now if I want to check whether it is working or not, so I have to write sorry, data dot head. You know how they work, so I'm not telling you that what is this head and all. Now, yeah, you can see the top 5 columns, sorry, top 5 rows from the data set is showing here. Okay, and column names are already assigned here. Okay, so we want to say the shape of the data. That means how many rows and columns are there. You can see 748 rows and 2 columns. All right, so this is a good shape. So now, if you just want to see whether this data set is biased or not, or balanced or not, better I say, it is balanced or not. Balanced on the sense, this you can see this is in this level there is 0 and 1. Okay, so 0 is, you can say, negative, and 1 is for positive. Okay, so negative review and positive review. It is like that. Okay, so just if we want to see whether it is balanced or not, that means in your data set whether the number of negative review and number of positive reviews are almost equal or not, or nearly equal or not. Okay, that is important. Otherwise, if it is unbalanced, then your model can become biased to a particular class. Okay, so do it data dot, that column name is level, right? Level dot value underscore count. Okay. So this helps you to see another thing also. Sorry, data dot label dot value underscore counts. So it helps you to see basically two things. First thing is we know, or we was assuming that there is two kind of levels, 0 and 1s, and there are number of positive review and number of negative review it is showing. Okay, so, and they are almost equal. So we can say it is quite balanced. Another thing we can see here, that is whether there is some other value available in the level column, which is apart from 0 or 1. In that case, we have to handle them, or we have to remove those rows. Otherwise, it will not remain a binary classification. It will become a multi-class classification. Okay. So, okay, this is we have done. Next thing we need to do is we can just remove the punctuations from this text, right? Because we need to do a minimum amount of pre-processing. So import regular expression, import string. Now we write a function. We already write it, so there is nothing to explain. What is this? Input read CSV. I have written this. Input RE. Text underscore no punct. We are creating a empty string first. Okay. Then we will assign the punctuation pretext to this variable like this by doing substituting. Okay, so re dot sub concatenate string dot punctuation plus closing box bracket. Okay, so if there is punctuation, we are going to replace it by empty string and we're passing text. Okay, then we will return the cleaned text. Sorry, we have taken what? Text with no punct. So that will return. Okay. Now data text underscore clean. We are just creating another column in the data frame. Clean equal to data this text column we need to pass apply lambda x column remove punct this function. We will pass this x. Okay, so run this. Okay, so let's see what changes have happened to this after doing. So how we can do? We can simply say data dot head. Okay, so you can see here it is showing, past 5 and last 5 rows from the data site. Okay, and you can see, text clean on new column is added to this. Okay. Yeah. So text, this column name, this text actually should be here over this column, and on this column it should be this text clean. Okay. So they are just due to this line, they are just move to the right side. So don't worry about that. Okay. Next, what we'll do tokenization, right? So import NLTK, and we know we need to download the pang for this. So it's with this itself I'm writing NLTK dot download. What you need to download is pang, UNPUNKT. Okay, so it is done. Next, we can do for we can do the tokenization. So from NLTK port word underscore tokenizer. No, sorry, tokenize. Okay, word underscore tokenize. Tokens equal to, we're taking tokens new variable. Okay, so tokens equal to this in the list you write word underscore tokenize, word underscore tokenize. We send some sentence to this. Okay, for sentence in data dot the text underscore clean, right? So we have cleaned this, so this column. All right. So now we can just check what effect the tokens, few tokens we can just check. So tokens, just for one sentence we are going to display. So you can see, yeah, one of the sentence is tokenized like this. So it is taking vertical pace. So I just try to print so that it will print it horizontally.
Sir, what is this sentence? SEN?
Sentence is a parameter we are passing to this word to tokenize function.
Okay.
Do you understood this?
Yeah, I understood, but like how this particular
How
function
we
is
are passing it? We are
from
using
where?
SE for send.
Okay,
Pardon?
okay, understood, sir. Understood.
Okay. Next thing we will do, we'll just go for converting everything to lowercase. So again, this is another old thing we have done previously. So we have tokens, so pass directly we will pass the tokens. Okay, it will return w dot lower So again, lower is the function which converts a string to lower for W in tokens. Okay. So this is the function we have already written. Now call the function lower underscore to tokens equal to lower underscore tokens. In what we are passing, we are going to pass tokens. Okay. For token in tokens. Okay. So let's run this. We got error. Let's say lower token is not defined. So some spelling mistake we are doing. Yeah, here is the here S is I have written the S, but here I have not written the S. So remove this S. Okay. List object attribute has no attribute lower. Yeah. So see return W dot lower W in tokens.
Tokens, sir,
Yes.
not tokens. The for loop.
If I write here token, then here also I have to make it token, right? So if I run this, no. So something is going wrong. Lower token is that there will be multiple tokens at a time we are passing. Okay.
Sir, in
So
bracket you write
we
down
will-
token, sir, when you are calling the function.
Here we should send token.
Token.
Okay. Yeah, now it can work. Yeah. So if I check for at least one row, I'm sorry, take this one. Okay, so you can see everything is in the lower case. Next, we are going for removing the stop words, right? So again, we know how to do it. We have to download the stop words first. NLGK dot download. What you have to download? The stop words. Stop words, right? NLTK dot download stop.
Download spelling, sir.
WNLOAD. Yes. Thank you. Okay. So stop words are downloaded. So from NLTK dot purpose import stop words, right? Then stops equal to stop words dot words. Sorry, no line. Stop words dot words in which language? English, right? So English. Okay. Now we have seen what is there inside it and all and stop word previously. So I'm not going into all these things. So simply I write function to remove the stop word. remove stop words. Okay, what we will pass to this lower tokens we have created. So that tokens finally will pass to this. Okay. Now filtered words equal to empty string we are creating. Sorry, not empty string, because we are giving tokens already. So list. Okay. Now for saint, or better you write some other s in lower tokens. Okay. Create a temporary list. Temp equal to a empty list. Then for token in S. Okay. For token in S, what we will do if token not in stops, right? I had created stops variable here, which have all the which have a list of stop words in English. So if token not in stops, it is not there in this list, then it is not a stop word. So we'll append it to this temp. Okay, so we'll do what? Temp dot append the token. Okay, and after that, before coming out of the outer loop, here I will append that temp variable, a temp list, to this outer list. Okay, dot append temp. Okay, so finally we'll return this filter words. Okay, so we just call these filter words. Sorry, equal to, calling this function, and we will pass lower tokens. Okay, and yeah, just let's run this. Filter word, remove stop word. Stop is not defined. Okay, I had not run this one first. Still F somewhere remains. Filter words.
Spelling.
Yes, it is done. Okay, so you can just check whether everything is happened or not. So you can check the length of lower tokens. So how many rows are there inside it? It will show 748. So we had started with 748 rows. So it is going well, you can say. Now, finally, to the text final column, we will add to the data. Okay. Text underscore set final. Okay. And what we will add here, we will add this filter words there. Okay. So that we will have a track on it in the data frame itself. So is dot join. So we are adding them as a a sentence itself. We are not adding them as a token. Okay. So join the send for sign in filter words. Right? And if we want to keep the tokens also, then just do the add another column to it. Tokens equal to the filter word. So understand, in the first one, in the filter word, the tokens are there, which will be just joined together, and as a sentence, it will be added in this column, and the tokens, they will be as it is, as a token, it will be, inserted into the data frame. So if we just see here, sorry, data dot head, you can see that changes have been done to this.
Sir, will you please share this code in chat?
In chat. So it's been a actually there is many codes already written, so it will take lots of time. Okay, so okay, this if I just reduce this size, sorry, 100%, then you can see the data frame here. We have 5 columns, but contents are not visible. Contents are not visible here. Okay. This, yeah. The final text, final tokens. Okay. So it is showing in the buffer way. And if you want to make it an interactive table, then you can see by clicking on that button. So you can see the original text, the labels original, then the plain text, the text, and finally what it looks like. Okay. Okay. I had not given space here inside. I think here. Okay. That is the reason it is concatenated all together. So it is text final, right? So yeah, now you can see here the spaces are coming. Okay. The tokens, here you can see the list of tokens. All right. So previously also somewhere I had written. Okay. So this is how much you have done. Then we will do some stemming and lemmatization. So we are going to use the Porter stemmer. So from NLTK dot stem import Porter stemmer. Okay. We create a variable, say PS, in short of Porter stemmer, and where we are just you can say it is a object of this Porter stemmer. PS is the object. Okay. Now we are writing a function def stem word. We are going to pass the tokens. Okay. Then root word equal to, we make a empty list, then for sign in tokens, we are going to use a temporary list. Okay, temp equal to this. Sorry. So in token. Okay, so temp is a temporary list here. Then we are going to check, is sentence in the token, or we can use here for better variable names t. Okay, now say for t in just a minute, for t in sentence. Okay, just a minute. Both the places I'm writing t, right? So here I write SCN. Okay, now we will do this for t in SCN. Okay, go ahead. If word don't need to do this. You can simply do the root equal to ps dot stem, right? Stem, what is there? T. So it will find the root of t. Okay. Then what we'll do? We'll append this t to this temp list. Okay. So temp dot append t. Okay, sorry, not t, root. Okay. So we'll get a list of root words which I need to append to the root words. Okay. Root words dot append temp. All right. Finally, will return. What will return? The root words. Okay. So if I just call this, sorry, first run this one once. Yeah. So root words equal to stem word. I'm going to call. Okay. What we will pass to this data from the data frame, right? Tokens. Okay. Sorry. Okay. So this is what we are going to pass, and we can. Okay. First, you run this. List of the as append append. Okay, so this is done. Now we can add this to another column to the data frame. So data frame, creating a column called system equal to this root words. Okay, and again you can just see the change in data frame, data dot head. It is going wrong, right? So that means our function need to be checked. First for loop, we are doing sentence and tokens. So sentence is going to be, the sen is going to be a list of tokens, no issue. Then T is one of the token from the sen, no issue. Then we are calculating PS stem of T, right? PS stem of T. After this also no issue, there should not be an issue. And append team dot append root. Right. Okay, I think when I created these, added these tokens, there something data frame in the data frame where I had added this token column. I need to check there. Yeah, right. This. So slow moving. Okay. Okay, let me just copy this function from my original one. Convert to lowercase is done. This is what we are doing, stemming. Same problem it is coming because problem is coming due to this token column, basically tokens column, right? So where I have generated these tokens and added that, I have to check first. Tokens equal to where? Sorry. Final text, right? So I have added, it should be lower tokens should be added. Final text is, yeah, final text is already after joining this, it is giving final text, right? So, okay, so it should be filter words. Yeah. Child. Yeah, now you can see in the tokens, the commas are coming. So this was not coming. That was the reason it was taking all the tokens as a single as a single string. So it was giving the problem. Sorry. Okay, now you can see the stems are here. Right. So, okay, so I'm not going to explain again this stemming things because in the previous discussion also we had discussed about the stemming. Now, do lemmatization also, so that you can see which one to use. Okay, so for doing this lemmatization, we have to download WordNet first. As I had told you, that lemmatization uses some dictionary. Based on that is that it finds for the it. Okay, somebody said that share notebook. Oh, let me see if I can share this itself. You try this link. I think this notebook will be visible to you. Okay. So, okay, so after this is done, then go for lemmatization. NLTK.download WordNet. Done. Then from NLTK.stem import WordNet lematizer. Okay. Then WordNet or say simply lematizer equal to, I'm doing WordNet lematizer. Okay. Then write a function def lem underscore words. We will pass the tokens lemma underscore word equal to empty list. Then so this something will be a same code will be used there. Okay. Or sen equal to tokens. Have a temp list. Temp for t in send if or not in stop. Okay, again it is checking. Okay, then root word equal to ps, not ps. Here we have lematizer. Okay, lematizer dot lematize. Okay, the function name will be lematize. Okay, it is t. It is t. Okay, temp dot append root word. No problem. Then root words equal to append temp. Okay, return the root words. So function is ready. Lemma equal word. Sorry, with lemma words. Lemma words. Okay. Unindent. Okay. Indentation problem. Okay, this is done. Okay, so here at this point, you can do multi-level of lemmatization. I kept one level of lemmatization, and here I have given what only T, but you can okay. So there is different kind of thing you can do here, but okay, without doing them, just run this and see what kind of result we are getting. So lemma words equal this, right? What we will send here? Data tokens. Okay, so it is done. Then we can just add this to the data frame here itself. Okay, so data new column we define say lemma, okay, equal to lemma words, and we want to check the data frame head. Now you can see here the stem words and lemma words side by side. Okay, then the pre-processing part is done. Okay, so we will move for our work. So first of the things we want to see what are the columns are there right now in the data frame. Okay, so you can see these are the different columns are being right now in our data frame, right? So first thing what we will do, positive and negative, we will create basically two empty list. Say positive equal to empty list and say negative equal to another empty list. Okay, now we'll go through the levels and we'll keep all the positives with positive and all the negative with negative. Okay, so if I write the code, you will understand. Okay, for L in data dot level, if L equals 0. So what we are going to do basically finally we'll add two columns to the database data frame. One column will be named as positive, another column will be named as negative. Okay, in case of positive columns, if the review is positive, in that column it will be it will be 1 and negative will be 0, and in the negative column negatives will be 1 and others will be 0. Okay, so that will do. First dot append 0 and make dot append 1. Okay, else or maybe elif L equals 1, then sorry, the reverse thing will happen definitely. Here it is 1, here it is 0. Okay, and finally, after doing this, we are adding this to the data frame. So pass equal to pass equal to negative. Okay, so and we will, okay, first let's finish this. Okay, you will while scanning string literal
Data dot.
yes. Oh, here it should be dot, right? And should be data dot level. Yeah, so it is done. So the just will reshape our data frame. Data equal to data, only few columns we will keep, all the columns we don't need anymore. So what we are going to keep here, text underscore final, then lemma we are going to use, then label, then sorry, was, then made. 1 minute. Okay, so after that we can just check what change have been made. Okay, so you can see the final text is there. We are not going to use that stem words. We are using lemma here, and labels we have taken, and positive and negative, these two attributes we have added, so we have kept them here. Okay, now we have to split our data set into training and test sets, right? So for that we have to install sklearn first. Okay, and then from learn dot model selection, we import trend test split. Okay, run this. Some model selection, model underscore selection, underscore selection. Okay, then we will create here data underscore train comma data underscore test equal to, I can just use this trend test split. First you need to pass the whole data set to this, then the test size. Now here, it depends on you that what percent of data you want to keep as your test data set. So as we have very small data set, so I am taking only 10% of my data as a text. Okay, then random state equal to any number you can give here. I can give here 40. Okay, so understand. So this 40 will fix the random state. So every time you will run this code, it will produce the same random number sequence. If you don't give the state,
today
every
Java
time
is
it
good,
will.
huh? Data analytics, how is it? Random. Hey, Prem. How are you? Why you are going, man? Not good, huh? It's okay. Okay. Hi, good evening. Thank you. Bye. Wish you all the best.
Sir, what is the role of this random state here?
Yes.
What is the role of this random state here?
Okay. We are randomly choosing 10% of the rows out of our data frame. Understand?
Random state this 40.
Huh?
Random state this 40 I am talking about.
Okay. This makes this random state fixed. If you don't give this, every time you will run this code, it will generate a different random sequence. Understand? And if you give this 40, every time it will take this 40 as the initial value or initial seed, and every time it will generate same random sequence. Clear?
So I can give here any random state number.
Yes, you can give any almost. Yeah. Yeah. So if you see here the detail, you can see regarding random state, anything is written, it should be written in this document. You can go there and you can check it out. Okay. So I think I made the doubt clear here. Okay. So this is done. Next, we have to do the deep learning part. Okay. So Keras is the deep learning library which is available here on Google Colab. So we are going to use this. Okay. So in Keras, there is a tokenizer class again. Okay. So which have these functions: fit on text, text to sequence, text to matrix, and sequence to matrix. So few of them we will use, and one by one we will go through them. Okay. So first thing is we have to collect all turning words. That means all the lemmas or unique lemmas, you can say, we are going to collect in a particular list. Okay. So all training words equal to word or tokens in data underscore frame lemma. Okay, so all the lemma I have told you, we are going to collect for word in tokens. Okay, so run this. Right. Then what we will do, training sentence length. So all the no, different sentences are having different length. So we are collecting all the sentence lengths in a list, which will be named as training sentence length. Okay. Training sentence length equal to, again we need to generate a list. So length of every tokens, right? And that means number of tokens are there in each of the review. Okay. For tokens in data train lemma. Understand? Next thing we will need is the training vocab. See here in the first one, we have collected all the words. Now from there, we have to create the training vocab. Okay. Training vocab equal to we are just shorted this list, then we're getting the set operation over all training words. Okay, so you understand what is going to happen. The set operation will return you the unique words out of all training words. Then this set will be converted to a list, and finally that list will be sorted in ascending order. Okay, by this sorted function. Okay, so we have generated the vocabulary, right? So next thing what we can do is the total number of words in our vocabulary we can just check out. Okay, print length of this, right? 2694. And if you see how many we had in the, how many words or tokens we had in the original book, tokens, it was more than 7,175. So it is reduced to this number in the and these are the unique words we have in our vocabulary. Okay, and another thing we can check, that is the maximum length of sentence. Okay, so max sequence length equal to max of this length. Okay, better I put it there. Okay, if I get this and if I print it here, yeah. So maximum sequence length, you can see there is 789. Why I'm doing it? We will need all this information later. Okay. Next is fit on text function. I had already told you that is available in Keras tokenizer class, which is used to update the internal vocabulary of the text list. Okay, we need to call this before using other functions like text to sequence or text to matrix, all these things. Okay, So first thing, what we will do here, we will import the Keras tokenizer, okay, or from, just a minute, yeah, from Keras dot pre-processing dot text import tokenizer, okay. And another thing, we have to import from this same place, from the same place, that is Keras preprocessing dot sequence. Okay, there is another package, sequence. We import pad sequence, pad underscore sequence. So why we will need this? Because we will find that all the sequence are not going to be in of same length, because all sentences are not of same length. So we have to pad them. Okay. Otherwise, when we will input them to the neural network, the neural network is having a fixed input size of the input layer. Okay. So there it will be a problem. So we need to pad and make all the sequence length equal. Okay. So what mistake I have done? Pad sequences. Yes. I think it work. Yeah. So here some of the thing we can do, like how many document count we can see, and all these attributes are available with fit on text. Okay, so let's first use this fit on text thing. Okay, tokenizer. Tokenizer equal to, take this tokenizer basically. Okay, number of words is one of the attribute. Okay, number of words equal to what? Length of training vocabulary. So this is the number of words we are sending to the tokenizer. Then lower equal to true. Okay, if some word is not in lowercase, it will convert it to lower. Okay, then char level equal to false. Okay, run this. Next is okay, so our tokenizer is ready.
So
So
why have you
tokenizer
used char level here?
dot,
Char level equal to false.
okay.
Sir, what is the role of char level equal to false?
I'm showing you. Everything is not possible. Char level is true. Every character will be treated as a token. Every character will be treated as a token if you make it true. Understand? And if you make it false, then your every word will be treated as this. Okay. Fit on text. Sorry. What we will send here? Data lemma, right? And dot to list. Okay. right? So next thing, we have the tokenizer ready, so we can view or we can display some all these things from the tokenizer once it is once we have fitted it or fit on text we have done. Okay, so let's see. Sorry, print, take the tokenizer dot document underscore count. So it will give us number of documents we are considering. Okay, so 748. So each of the review is a document. All right. So we had 748. Then what other are there? Let me check. Automatically it is not caught. Yeah. Say we are choosing word count. Okay. So here you can see for every word, how many times it is appeared in the on over all the documents. It is just given. Okay. So all that stats you can see. Then word index you can see. That means which word is at what index that it will show. Okay. You can see movie at the 1st position in of the list, film at the 2nd position of the list, and so on. 0, 1, we have not removed numerics, so they have also came here. Okay, 0 is on the 3rd position, 1 is on the 4th position. Okay. And so all these things you can see. Okay. Then the given a corpus of document we have, right? So text to sequence and assign integer to the words. Okay, so we can use the text to sequence from the keras. Okay, so for this the maximum sequence length we can define, like in what to bake we had done, maximum sequence length we had given something like 100, right? So here also we can do that. Okay, so maximum sequence length we already have something here. You can see here this is huge, so we don't want to use that. Okay, so maximum sequence length equal to, say, assign 50 and embedding dimension. Okay. Embedding dimension, say we are giving here 300. Okay, so so these things basically parameters for a neural network here. Okay, so based on your data set you can change them and you can see how result is affecting, okay, with increasing and decreasing the dimensions. Okay, so
So,
now
but for now, how you are setting these two parameters for the given data set?
randomly.
Okay, any value we can give?
Yeah, I've given any value.
Okay.
These things are very hard to optimize. Right, you can't say that this is my optimum value of dimension, this embedding dimension. Okay. Maximum, sorry, training sequence equal to, we have to take tokenizer dot text to sequence data underscore train lemma to list definitely. Okay, so let's run this. Again, some spelling mistake I have done definitely. Tokenizer object has no attribute text to sequence sequences. It should be. Text also S. This is not supported between instances of intent list. Training underscore sequence to tokenizer text to message data train. Why this error is coming? Greater than equal to not supported between instance of int and list. So there is some number of words and I stick and do. Just a minute, let me check it here. Okay, I think somewhere it is, this error is coming from this actually, what data we are passing. In the we need to troubleshoot. It will take a long time. So I'm just leaving this here. I'm just continuing with this one. Okay. So up to this, same thing you can see in this notebook. So if I run this, yeah, here we had, right? So we have, I think, missed something in the pre-processing, maybe, or maybe something happened somewhere. So it was giving error. So right now you can see that training sequence equal to tokenizer dot text to sequences, and this function we need to pass the attribute or this lemmas basically as a list. Okay, then you can see you are printing the sequence generated from the text or training sequences. Okay, so it is going to print this sequence is generated, okay, from the training sequences, and then train one word index equal to tokenizer word underscore index. Okay, so this gives you the train word index as well. So that I had shown in the previous case also here. So index of the different words. Okay. So and total unique how many words are there? We have already seen it. Okay. Next is the sequence pad, right? So I have told you that we will have to pad the sequence, and for that thing we have a pad sequence function. Okay. So if you see here, we are not using them. Okay. So before we go for padding the sequence, what we are doing here, we are just initializing a matrix of a dimension we are considering, that is, you can see here, train word index length. So this length plus 1, and embedding dimension what we have given, that is embedding dimension we have given is 300. Sorry, no, if you see here, we have given is 300, right? So this, okay, let's delete this. Okay, so with this dimension, we are creating a empty matrix, np dot zeros. So sorry, a matrix of this dimension you can see here, with all initialized to 0, all elements are 0. And why we are doing this? After that, we will initialize the embedding weight at the time of training. These weights will be changed or updated. Understand? So I just created this. Okay. So you can see here the total number of words we have in the vocabulary is 2460, and we have just passed it by plus 1. So 1 row extra we had created. Okay. So that is the requirement of the algorithm function. Okay. So now the CNN train model. So for this thing, first thing what we need the train CNN data, right? So first thing, as I have told you, we have to pad the sequence if they are uneven in length. So we are giving the training sequence here. Okay, you can see the training sequence is visible here. Okay, and maximum sequence length what we have defined, which is 50. Okay, so max length equal to 50 we are entering. That means max length is 50, and training sequence we are sending to pad sequence. So what it is doing, you can see it is padded with 0, which sentences does not have this 50 number of words, you can say. Okay, and it is creating a matrix like this. Okay, I think it is clear. So this is what I'm preparing the data for my CNN model. Okay, then test sequences equal to tokenizer. In the same way, train sequence I have generated. So test sequence also we have to generate. So you can see the test sequence, test CNN data is also padded. Okay. So that's one. And level names we have defining here positive and negative. All right. So y train equal to data train levels name dot values, and y test equal to data test and level names and values. These are very common thing we do almost every classification model either in NLP or any other domain everywhere, right? So this will be needed to evaluate your model later. Okay, to compare that predicted level and what was the original level. Okay, so X train equal to this train CNN data what we have prepared, we have put it here, and Y train equal to Y underscore train. The levels are put it here in this. All right. Now we will move to the CNN model. So in CNN model, there are basically 4 parts we have to write. One is the embedding layer. Another is input. It is used to initiate the Keras tensor. Another is the convolution class. Here we are going to use 1D convolution. Okay, and global max pooling layer. That is also where, as the if convolution is one dimension, definitely the max pooling is going to be used in 1D only. Okay, so this is the thing. So that thing will look like this. We will have input channel, okay, which input, if you think this is a neural network or CNN network, okay, just a minute. Okay, then this input is coming from the input layer. It will go to a fast convolution layer, okay, and then this will go, the result of the convolution layer will go to the 1D max pooling layer. Then there can be again multiple convolution layer, max pooling layer can be there. Okay, and finally we will have some fully connected layer. In the fully connected layer, we also call it as dense layer. What happened? All the levels, all the neurons of different levels are totally connected, fully connected in these layers. Okay, and finally it gives you the output. This is the rough concept of the thing. Okay, now if one by one we'll go. Okay, so first thing is the embedding class. Embedding class is an inbuilt class available we have in Keras for CNN. Okay, so in embedding class we will have different arguments. So what you have to pass, like input dimension, output dimension. So if you give the input dimension to something, the input layer will be automatically take the inputs in that dimension. If you define some output dimension, the output will be given to you in a particular or that chosen dimension. Okay, so this is the thing, then embedding initializer. Okay, so we have already initializer matrix generated and kept ready. Embedding regularizer. So this basically regularize the embedding matrix. Okay, then embedding constraint mask 0 and many other there are there. So I'm not going to going to say all these things. Okay, now you can see how it will look like when you will write the code. It will be exactly like this. Embedding layer is the object, embedding is the class, and what we are passing to this sorry, embedding will be the function derived from that class. Okay, embedding. Then number of words we are passing, that we have to pass here. Embedding dimension we have to pass, right? Then weight, if we have generated some weight matrix, then we can pass these weights. Okay, then input length. Input length you all know, right? What is our input length of our data? And try enable is false. Okay, so these are the things are there. Try enable, I have forgotten. I think I've forgotten what was it. This is, I think, for used for multiprocessor thing. Okay, so whatever. Okay, so next, what will happen? This embedding layer will take the input and it will just give you the embedding or embedded sequences. Okay, it will give you the embedded sequences. Now what we will do with that, right? So if it will go for the sequence, will go for the convolution layer. In the convolution layer, you will have some kernels. Okay, so 1D kernel I have not shown here. In this I have. Yes. So this is your kernel, okay, and this is your embedding sequence. So this kernel will move over this like a sliding window, and it will generate some value and it will be kept here. So you can see here, if you have a length, input length of 1, 2, 3, 4, 5, and your kernel is of size 2, your output is going to be of 4 length. Okay. So you can understand that convolution layer will do two things. One is multiplication of your input with the kernel, and somewhat little bit it will reduce the dimension of the input. And if you just add some padding layer here, if you don't want to reduce the dimension here itself, then you can have a extra backend window or pad window here, a pad cell here, input cell here. So it will be pipe again. Okay. So this is what it does, the convolution, right? So we will see that we will define different filter sizes for the training of the thing. Then on the convolution layer, and then in the max spooling, what happens? In the max spooling, whatever you will give, whatever dimension you will give. Say here you can see 4 by 4 dimension is given. So it will take the 4 by 4 area of your output of the convolution layer thing. What the matrix what you will be output from the convolution layer, and out of this area it will choose the highest or maximum number okay, to represent this area. Okay, so if you see here, this is a max of 4 by 4 part, right? This 4 by 4 part. So what is the maximum number here? 9. So this whole part will be represented by 9. So you can see that from your 4 by 4 area, that means 16 element is going to be replaced by 9 by the maximum layer. So what happens in the neural network? By doing this, you can see here, input layer, you are giving, you are having these many neurons, and then the hidden layers, the number of neurons are less. So how this can be done? Okay, or better if you say the dimension reduction happens here. Okay, so basically the dimension reduction happens here. Okay, so go ahead. Yeah, so first thing what we have to do, we have to write a function called convenate function. Okay. Okay. So whatever function name you want to give, you can give. CNN function you can give. Okay. So I have given here convenate. The function name is given convenate. Okay. And for doing this, we have to call different layer from the Keras library. You can see. From Keras.layers, what are the things you are calling? Dense layer. I have shown you in the diagram, dense layer is needed at the end. This is fully connected layer. This is called what? Dense layer. Okay, this is called dense layer. Okay, so dense layer we are calling from the Keras. Then drop out, then reshape. Sometimes we may need to reshape our data inside the neural network itself. Okay, then flatten. If we want to flatten our data, then concatenate input conv-1D, that means 1D convolution network we're calling, that will be used in convolution layer. Okay, then max spooling layer we're calling, then embedding we're calling. Okay, you can you may remember that we have not done the embedding task using what to back here, because we are going to use this embedding. Okay, which is available here. Okay, then Keras.models, we are just importing the model. So this is the model import from sklearn library. I think you people are quite familiar, right? So here from Keras we are importing. Now define this. Now, what are the things we need as the input for our combination CNN? Okay, we need the embeddings. We need maximum sequence length. We have already available it, right? I have calculated. Then number of words we are passing, we already know. Then embedding dimension, we already know. And levels index, we already know. We have shown it right previously. So all these things we will need in different layer. Now come layer by layer. First is embedding layer. Okay. So there is embedding class from where we are getting this embedding layer. Okay. So you can see this embedding we have imported from class.layer. So okay. So we are creating object here, embedding layer equal to embedding. Number of word we need to pass, embedding dimension we need to pass, initial weights we can pass. Okay. Then input length we already know, and again this train enable. So we are making it false. So train enable is false. Okay, we are not enabling to train it. Okay, so this object we created, then input function. So sequence input equal to input. It need the shape, what in input shape. So maximum sequence length we are giving, and data type also we are defining it is in 32. So input function also we have defined. Okay, then embedding sequence. Okay, so you should understand that this is what we are writing a function definition. Okay, so embedding sequence is equal to embedding layer. What we need to pass to this embedding layer, we pass the sequence input to this. Okay, so that we get the embedding sequences. Now we make a empty list called cons. Okay, we'll need it later for the convolution layers. Okay, and filter size is also we are maintaining here multiple sizes of filter. Filter size of 2, 3, 4, 5 up to 6. So 1 to 5 filter size we are considering. Now for filter size, for each of the filter size, we are going to call the conv 1D. Okay. Okay, so every time we're going to call this conv 1D for each of the filter size. I think you understand who have a little bit knowledge of this CNN. So this is what convolution layer. From where we're getting it from Keras library, right? So for each of the filter we're using this and filter. How many filters? 200 filters. We are fixed it here. Okay. Then kernel size equal to filter size, right? So you should understand one thing. These kernels and filter are mostly used alternatively, but there is difference. I'm not going into that right now. And we are using an activation function called ReLU. So okay, then embedded sequence we are going to use with it. Okay, so after we are one convolution layer is created here. Okay, then we are doing max pooling layer. Okay, so global max pooling 1D we are calling with simply this convolution layer output we are passing to this. Okay, and cons append this L underscore pool. So this cons will have basically 5 models. One model is for filter size 2, another model is for filter size 3, and up to 6. Okay, clear? Now L underscore Mars, this is the Mars layer, another layer I had told you. Concatenate this cons to axis 1. Okay, so actually what is going to happen, understood? Here we are going to make 5 layers. Okay, Can I write it something? Okay, it is not visible. It is visible. Okay. Okay. So if I just let me take. Okay, no problem. Okay, so let me take the pen. Yeah. So what is happening at this place? At this place, we are doing one convolution layer, then one max pooling layer. Okay, this convolution layer is having using sequence filter length of 2, and max pooling layer is simply using, you can say, we are not giving anything, we are not passing anything, we are just doing max pooling. Okay, then another convolution layer with filter size 3, then again another max pooling layer, another convolution layer, another max pooling layer. So you will give input to this, it passes through all these. Finally, in the final max pooling layer, whatever it gives, which is whatever it gives, that is going to be used for the LMARS thing. Understand? So this is the thing. Okay, so this happened. Then we go for dropout layer. Okay, so how much we can just percent we can define what percent we want to drop out. So 0.1% is going, 0.1 we are going to drop out from the LMARS. Then we are going for the dense layer. In the I was telling you, in the dense layer, every neurons are connected with other neurons or the other layer. Okay, and we are also providing here the activation function, which is ReLU function. Okay, and again after that you can see the same X is going to keeping updating, right? First it drop out, then it got a dense, then again it is getting a drop out. Okay, and finally we are going for the prediction layer. Okay, which will give you the final prediction, which is again dense. Okay, and it is this X is used here with dense level index. Level index we had already level index. We previously we had defined this level index. Okay, and activation is here we are giving sigmoid because we are doing a binary classification. So sigmoid is going to behave good with binary classification. So we kept a sigmoid here. Okay, then model equal to finally this model. You can see this model we are calling here. We are using here the cross model represent the actual neural network. Okay, so model equal to model sequence input and this prediction. So this prediction is having the final dense layer. Okay, so we are putting it here. Okay, then model dot compile loss equal to binary cross entropy, and optimizer is Adam. Okay, then metric is the accuracy metric. Okay, and model dot summary we are going to print return model. Okay, so this is the function which you can say which is going to behave or do the work of CNN. Okay, then here see model convolution, this our function what we have written. Then we are sending what the training embedding weights we had calculated previously. Maximum length we had initialized. Okay, length of training word index we have the training order index we had printed previously, plus 1. Okay, then embedding dimension also we had defined, right? Then length of list of name levels. That means it will give you 2, right? So if we run this, this is the summary of the model is coming out here. Okay. Okay, in the same sequence, so in what sequence we had written our function. Okay. So okay, we'll go ahead. Now we can just define number of epochs. That means how many iteration you want, and batch size also 14. Now we do what? Model.fit. This is the main thing. Fitting the model over your training set. Okay, still now all these things was just configuration of the CNN. Now we are going for training. So model.fit, we send the x underscore train, y underscore train, epochs, we have initialized this to 3. Okay, 3, you can see here. Okay, validation split, we are keeping validation also with 1% data from the training set. Okay, shuffle is true, batch size equal to batch size, which is 34 we have defined. Okay, so train the model. See, first epoch, then it will go for the second and third, then the learning will be completed. So this epoch is basically, if you change this, to 5, 10, you will find that your accuracy is also changing with the number of epochs. Okay, because more it will be changed, definitely up to optimal level, optimum time, you will find that it is learning better. Okay, after that, the accuracy will be, remains same. You can see here, the first iteration, this was the accuracy. Second iteration, this was the accuracy. So accuracy is not changing here in this case, in our case. Okay, so and loss also, if you check here, initially in the first iteration we had a 6932. Okay, the loss, that loss after the second and third, in the second and third, amount of loss are also same. This accuracy are also same. Okay, and value loss, if you see here, yeah, this is going to decrease in every iteration. Okay, so you can say that 3 is good for this case, for our case. Okay, now prediction. So we want to predict using the test CNN data what we had prepared previously. So the predictions are stored in the prediction. Okay, level equal to zeros and ones. Then prediction levels. Okay. Now here is the overall accuracy. That is, you can see data.test.label equal to prediction prediction was the label, but length of prediction level. Okay, so how many times these two are same, divide by the number of prediction levels. Okay, it is 41% accuracy it is given. Okay, so how many in the test result, prediction result, you can see this many 44 44 times it is predicted that the results are negative, and 31 times it was predicted as positive. Okay, then you can go for confusion matrix and other thing. Okay, because as you are doing, just a minute, I think you have you have the unmute permission. Now you have it. Okay. So
Hello. Hello, sir.
In the previous cell, that filter is shown. Dimension is 2 in that cell.
Just a minute.
Filter of
In
dimension
which
2.
cell number? Cell number?
Previous cell, where that filter is shown. It is shown size of filter was.
Okay, and in the function, you mean here?
Yes, above this cell it was shown.
Yes.
Here. And above this also one that you have shown it is scrolled and that size is from 6, that size is to 4 or to 5 somewhere. Previous cell, just previous cell to
In
this.
some diagram or previous cell in the code?
In the code. Before the model is trained. Before the model is trained.
Model is trained here. Model.fit. Here it is training.
Before that, initially that we move that kernel, no?
And just a minute. Before that, you said filter size. Before that, I don't think anywhere we have.
Here before that, this diagram was there. This one of the layer is there. Before this, there is one layer. This one. From 5 dimension, 5 size, you are getting 4 size. So that was with that moving that filter.
Okay.
Moving that filter.
You are speaking.
Here. So what is my question? That is 1, 2, 3, 4, 5. These are the lemma, means vector of lemma or what? Means that I did not get.
Yeah, vector of lemma. Vector of lemma.
Vector of
lemma. Yes.
It should be vector of lemma, and this kernel is something like 0.212, 0.2. So what does it mean?
Okay, this filter I am writing here. If you go to my code here, filter sizes.
Right.
So basically, if I give a filter size 2, it creates a filter of 2 by 2. Okay.
Yeah, it will create 2 by 2, 3 by 3, 4 by 4 like that.
Correct.
Yeah,
but I have shown it in 1D.
But here this 0.2 means what? That I did not get. This 2 is clear. Means either it can be 2 or 3.
This is basically these values are not given by us. Okay. This Keras library chooses this value and optimizes them.
So these are given somewhere. That is, these values should be applied. I mean, in some documentation or somewhere, that means it can be a kind of threshold value.
You can see the Keras. I understand. You can see the Keras documentation that how it decides these filter values.
Okay. Means some kind of threshold it is actually.
Definitely. So during the learning, it learns this value. Initially it runs this value. I have to also check basically. I have never searched for this how it is deciding this initial values.
No, actually it is means not that easy that that convolution network and all means very lot of vocabulary is there and so many parameters that I know somewhere I have used it on images. I have used it. Okay.
Yeah.
Thank you.
Sir, I have one query. Sir, in this dense layer, in the same cell, this dense function where you are calling dense label index activation equal to sigmoid function you are calling here. So, sir, here you said that the sigmoid function is good for binary data. Means since we have binary labels, so you are using sigmoid function. So, what activation function we can use in case of multi-label?
Okay. Yeah. Why I said this is good. The sigmoid will also can be used for multi-level. There is no doubt. Okay. Now what is the good thing with the sigmoid? even if I use this for binary, it works better because it is a car. It is not a simply step wave kind of thing. Understand? So even for the binary classification, we get the flexibility of the car.
Okay.
Understand? So the same sigmoid you can use for multi-level classification.
Okay, sir. Okay. Thank you.
But in that case, that for every label you will have to apply it multiple times that way.
Which one?
PG. Yeah, means in that case, if you are using sigmoid, means for every label you will run one prediction, because multi-label he asked question.
Multi-level is multi-class classification.
Multi-class classification. So for class 1, one sigmoid. For class 2, another sigmoid.
No,
It
no,
is
no,
like that.
not like that. No, 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 no. The same sigmoid, when it is multi-class classification, it basically gets the threshold, the different threshold for different class on the same sigmoid car.
Okay.
We use categorical cross entropy in case of multi-label.
And sir, why are you passing 128 inside the dense function here?
Yes, sir.
Yes, sir.
This is basically your number of input. Is it? No? Yeah.
So how in advance it is known that
Here
number
you
of
can see
inputs is 128?
I think that is number of layers, dense layers.
No.
Can we know in advance that there are this much of layers in advance?
Yes.
How can we know that there are this much of layers, 128 of layers in advance? Or we can increase or decrease this layer size?
Yes, yes. You just see this help of dense, here it will be given. How you can define the number of neurons you want in a layer.
Okay, okay.
Okay.
Sir, in CNN model, is there any, is it necessary to do all these pre-processing of data, like tokenization, removal of stop words and all? So is it mandatory?
After tokenization, you have to do, you have to get the tokens, then only it will work for the embedding, right?
And
if you don't want to do, then every sentence will become one single vector, and that can be given as input. But I don't think that will give you a good accuracy. You understand? There is no concept of word. You are just making all the sentences a vector. Understand? So your features, one sentence, one feature kind of thing will happen. So where it will not get the generalization.
And sir, what can we do to improve the accuracy? Because here we are getting 41% accuracy. So what we can do to improve the accuracy?
Yes, there are many things we can do. We can see number of approaches we can increase, but here not looking like a pass. So we have to go in the preprocessing part, or in the we can change the number of filters here. Okay, we can. This is basically if I just decrease the number of filters here. Okay, that means number of convolution layer I am decreasing. Yes.
Can I add answer?
Just see what is happening. You can add just a minute. Let me show you. If I make 3 convolution layer and 3 max pool layer, we have 5 now. So I'm making it 3. Okay. Okay, I can see that Sriparna ma'am is already waiting. She had joined. So, okay, did you get any change in the result? No, it is, we didn't got any improve. Okay, let's stop this discussion here because Dr. Sriparna Shah ma'am is already waiting. Okay, and you take a short break because it has been a long time we are discussing. Okay. Madam?
Yes, so when will you start? Am I audible?
Yes, ma'am, I can hear you. Should we take a short break?
Yeah, sure. So
Is that okay with you?
yeah, I'm fine with this. Yeah.
This maybe six. It will be good at 6:25, I think.
Okay, sure. So I am also logged in from WebEx 7, okay? So WebEx 7 is also the same, yeah.
Yeah, it is okay. Your video and audio both are okay, so there is no issue.
So we'll start at 6:25, yeah.
Okay. Okay, so we'll start at. Okay, so somebody is requesting for 6:30. Actually, ma'am, this time they used to move from their office to home.
What time?
6:30. Let's do it 6:30.
Okay, okay.
Sorry, you are going to wait.
Sir, can you please share this notebook? I think the one previously which you shared is not having the code. Or on mute, sir.
Yeah, we will. I will share the final code. Somebody was asking.
Yes, sir. So is it gonna be on the canvas or?
No, through GitHub I will.
Okay, sure. Thank you.
So it is already 6:30 and we are waiting for Suparna madam. She left. Let's wait for her. Oh, sorry. Ma'am is online. Just a minute. Okay. So, okay. Let me introduce Dr. Suparna Shah.
Hello, am I
Dr.
audible?
Suparna Shah is. Yes, ma'am.
I am
Am I?
audible, no?
Yes, I clearly.
Okay, thank you.
Yeah. So Dr. Suparna Shah received the MTech and PhD degree in computer science from Indian Statistical Institute, Kolkata, India in 2005 and 2011, respectively. She is currently an associate professor in the Department of Computer Science and Engineering, Indian Institute of Technology, Patna, India. She is the author of a book published by Springer. She has authored and co-authored more than 290 papers. Her current research interest includes deep learning, natural language processing, machine learning, information extraction, text mining, bioinformatics, and multi-objective optimization. Her H index is 30 and total citation count of her papers are 5,221 according to Google Scholar. She is also a senior member of IIIT. She is the recipient of late Rashi Roy Memorial Gold Medal from the Indian Statistical Institute for outstanding performance in MTech Computer Science. She is the recipient of Google India Women in Engineering Award in 2008, Nashi Young Scientist Platinum Jubilee Award in 2016, Bard Award in 2016, IIT Young Engineer Award in 2016, SARB Women in Excellence Award in 2018, and SARB Early Career Research Award in 2018. She is the recipient of Duo India Fellowship 2020. Then Humboldt Research Fellowship, in Indo-US Fellowship for Women in STEM, Women of Overseas Fellowship Program in 2018, and CNRS Fellowship. She had also received India for EU Fellowship for the European Union to work as a postdoctoral research fellow in the University of Toronto, Italy, from September 2010 to January 2011. She was also the recipient of Erasmus Mundus Mobility with Asia Fellowship for the European Union to work as a postdoctoral fellow in the Heidelberg University, Germany, from September 2009 to June 2010. She had visited University of Caen, France, and visiting scientist during the period of October 2013 to December 2013, then May to July 2014, May to June 2015, and University of Mainz, Germany, as well as a visiting scientist from April to September 2016, April to August 2017, University of Kyoto, Japan. As a visiting professor from June to July 2018, she won the Best Paper Award in Clinical NLP Workshop, Calling 2016, and IEEE IndieCon 2015. International conferences on advances in computing and communication and informatics. So we welcome Dr. Siparna Shah Madam to continue with the session. Her topic is multi-objective approaches for summarization problem using bio-inspired algorithms. So, Madam already shared her slide. I wish our participants will enjoy and have a good time with this lecture. So, Madam, please, you can continue.
Yeah, so hope I am audible.
Yes, yes.
Hello?
Yes,
I'm
ma'am.
audible, no?
Yes, you are audible.
Yes, ma'am. Clearly.
Okay. So first of all, thank you very much for inviting me in this particular occasion. And thank you, Dr. Bhaskar, for this nice introduction. So today I would like to talk on summarization systems. So basically, you know, summarization systems are a part of natural language processing, and it is a very important tool for natural language processing because there are many tasks which can be easily solved by using the summarization systems. So I will discuss about some recent approaches for summarization systems, and mainly I will discuss about some multi-objective optimization based approaches which are utilized for solving the summarization problems. So I will start a brief introduction of the some of the optimization problems. So you know, optimization is of two types. Either we can have a single objective optimization or we can have multi-objective optimization. So in case of single objective optimization, there is only one objective function. Hello. Suppose you want to buy a car. In that case, maybe cost is an objective function. So you know that this is an example of a single objective optimization where we are optimizing a particular objective function. But if we have multiple objectives, like suppose we want to optimize cost and comfort both. In that case, this is basically called a multi-objective optimization problem, where we are simultaneously optimizing multiple conflicting objective functions. And why we are saying conflicting? Because you can say that cost and comfort are two conflicting objective functions. So if you want to optimize cost, then comfort will be compromised. And if you want to maximize comfort, cost will also go high. It is not possible to simultaneously optimize cost and comfort both. Like it is not possible to minimize cost and also maximize comfort at the same time. So this is an example of conflicting objective functions. And this type of problem statements are called multi-objective optimization. So you can see that in case of multi-objective optimization,
Madam, I think you are on mute.
hello, am I audible now?
Yes.
Yes.
Okay, I don't know. I think I have some problem with my speaker. Yeah, sorry. Yeah, now I hope I am audible.
Yes, ma'am.
Yeah. And you can also see my slide now. I am in slide disadvantages of multi-objective optimization.
Yes, ma'am.
Yes.
So basically, as we have to simultaneously, so if there will be any problem with the audio signal, please message. Okay, just you can type. I am checking this chat box as well. Yeah, so basically, you know, in case of multi-objective optimization, as we are optimizing multiple conflicting objective functions, like for example, here we are maximizing safety and minimizing the breach cost. Suppose we want to, there is a breach construction is going on, and there are two objectives. We have to minimize the cost, but we have to maximize the safety. But these two are conflicting objective functions, because if you want to maximize safety, then the cost will also go high. And if you want to minimize cost, then safety will be compromised. So this is an example of a multi-objective optimization problem, and it is not possible to get a single solution which can simultaneously satisfy both the objective functions, like which is optimal for both the objective functions. It is not possible to get a single solution which is optimal for both the objective functions. Like here, if you can compare solution 1 and solution 2, solution 1 is better with respect to safety, but solution 2 is better with respect to cost. Similarly, solution 3 and solution 2, solution 2 is better with respect to safety, but solution 3 is better with respect to cost. So we cannot say that solution 1 is better than solution 2 or solution 2 is better than solution 1. So basically, solution 1 and solution 2 are called non-dominated solutions. And the set of all the non-dominated solutions is basically called Pareto optimal set. So at the end of multi-objective optimization, our aim is to produce a set of non-dominated solutions which is called the pareto-optimal front. And now basically, unlike the single objective optimization, in case of single objective optimization, we always get a single optimal solution. But now in case of multi-objective optimization, the user is given a set of solutions which are pareto-optimal in nature. And now depending on the need, user can select a single solution from this particular pareto-optimal surface. So that is another flexibility. So user is having the flexibility in choosing amongst the solution set based on user defined criteria. So what is the formal definition of multi-object optimization? So multi-object optimization can be formally stated as we have to find the vector of decision variables which will satisfy some inequality constants and the equality constants and simultaneously optimize some objective functions. So here we are simultaneously optimizing m number of objective functions, and these m number of objective functions are basically conflicting in nature. So there is no concept of global optima. Rather, we are getting a set of trade-off solutions which is called the pareto-optimal set. So you can easily see from this particular figure, here there are two objective functions f1 and f2, both are of maximization type. And now by simultaneously maximizing these two objective functions, we are getting a set of solutions in the pareto-optimal surface. Solution 1, 2, 3, and 4. Now if you compare solution 1 and solution 2, you can see solution 1 is better with respect to f2, but solution 2 is better with respect to f1. So we can't say that solution 1 dominates solution 2 or solution 2 dominates solution 1. So these two solutions are non-dominated to each other. And the set of all these non-dominated solutions is basically called the pareto-optimal surface. But if you compare solution 5 and solution 2, so solution 5 is basically dominated by solution 2 because for both the objective functions, solution 5 is having lower objective functional values compared to solution 2. So if you see f1, solution 2 is having lower f1, basically solution 2 is having higher f1 values compared to solution 5. Similarly for f2 also solution 2 is having higher f2 values compared to solution 5. So basically 5 is dominated by 2, 3 and 4 but not by 1. So compared to 1, solution 5 is having better f1 values and solution 1 is having better f2 values. So now let me discuss about the problem of summarization. So as I mentioned, the summarization is an important problem in natural language processing. Mostly summarization means the text summarization. So suppose there is a set of documents given and now we have to generate a compressed version of the text document. So now what do you mean by document? Yeah, document could be a set of tweets, it could be a set of web pages, or maybe we are considering a single document which is consisting of multiple sentences, or we can also consider there are multiple documents having multiple sentences. So basically our task is to consider multiple sentences and then we have to create a compressed version of the text document. That should be concise, relevant, non-redundant and representative of the main idea of the text. So a text that is produced from one or more text that conveys important information in the original text and that is no longer than half of the original text and usually significantly less than that. So basically we are producing one or more text that conveys important information in the original text and that is no longer than half of the original text and usually significantly less than that. That is basically the summary. So why summarization? Because internet has provided large collections of text on a variety of topics. So nobody is having time to go through all the documents. Suppose a particular event has happened. So suppose a particular event has happened and several newspapers are reporting about the event. Now we do not have time to go through all the newspapers. So basically we want to generate a summary considering the multiple newspapers. That is one application of summarization. So just to reduce the just to reduce the processing time and so that the user can easily get the important concept in reasonable amount of time, summarization is important. So internet has provided large collections of text on a variety of topics. There are large number of electronic documents are available, and users get so exhausted reading large amount. Users face difficulty in finding the relevant information. So solution is to generate a summary. And then from the summary, basically, you know that in the summary, we have to select the important sentences. So automatic text summarization system is needed that can compress information into shorter length, that must follow coverage of information, non-redundancy, information significance, and cohesion. So like there should not be repetition of information. So if a particular information is present in a particular sentence, the information should not be presented, should not be repeated in the summary. So basically we have to compress the information. We have to cover the entire document. Sentences should not be redundant to each other. And also cohesion should be also be there. So there are several goals of the summarization systems. Like summarization helps us in saving time. Summarization helps in compressing the large information. By saving time means, as I mentioned, that suppose a particular event has happened and there are several documents which contain the information about the particular event. But now nobody is having time to go through all the documents. So maybe we can simply generate a summary and the user can go through the summary to understand the event. That way it can basically save time of the users. It basically helps in compressing the large information. It helps in active reading. It is very easy to implement. It helps in decision making. Also, it highlights the central theme of the document. So there are mainly two types of summarization systems, extractive and the abstractive. So in the extractive case, we are selecting a few relevant sentences from the original document. So relevance of sentences is decided using sentence coding features like sentence position, similarity with the title, etc. So here basically from the name itself we can understand that we are simply selecting a subset of sentences from the original document to generate the summary. So we have to only somehow select, it is a kind of optimization problem. Given n number of sentences, we have to carefully select a subset of sentences, maybe capital M. M is obviously much less than capital N. And then these new sentences basically will form the summary. This is called the extractive summarization. Then there is an abstractive summarization. So in case of abstractive summarization, we are basically rewriting the sentences. So if the original text is having some sentences, then there is an abstractive summarizer, and the abstractive summarizer is basically somehow first selecting some important sentences, and then those important sentences are paraphrased to generate some new sentences. So this requires natural language generation or the reconstruction of the sentences. So this is the abstractive summarization. So there are two types of summarization systems, extractive and the abstractive. So extractive is only responsible for extracting. Extractive is only extractive is only selecting the important sentences from the original document.
Excuse me, madam.
Yes.
Ma'am, in case of summarization, there are suppose one event occurred, okay, and somebody is being asked to summarize it. So somebody may summarize it in perspective of scientific summarization or legal point of view. Then how can we conclude that we want, that means opposite party want this summary? That means are you getting what I'm saying? That means summarization is of very much various sides. That is news summarization, like legal summarization, scientific summarization. So much types of summarizations are there. But let one event occurred and we are being asked to summarize it. then I may summarize it in the point of legal view or any biological summarization, but from that event, another thing can be summarized. So I think ambiguity occur or what? That I'm not getting.
Okay. Yeah, I got your point. So basically, what
Yes.
type of, basically sentence selection is in your hand. Like when you will be developing the model, you can define the objective function like that. Like if you want to select the sentences which are more relevant in terms of biology, which are biologically more relevant, which contain more information related to biological concepts, then maybe you can accordingly define your objective function. Are you getting me? Like suppose you want to,
Yes.
for example, if you want to develop a opinion oriented summarization, then maybe you can put more emphasis on the sentences which contain some opinions. Okay. So basically that way you can define your own objective function, and basically it is a sentence subset selection problem. No, so you have to
Yes, ma'am.
define some objective functions, and based on those objective functions you have to carefully select a subset of sentences. So now how
Okay, ma'am.
you will design your objective function, that is in your hand. So depending on the problem statement, you can define your objective function. So for example, when we have worked on the microblog summarization, like the tweet summarization. Okay. So
Yes.
in that case, our focus was to help the rescue team. Okay, like suppose there a disaster has happened, and during the disaster situations, people used to stay connected with each other through the social media platforms. Like they used to tweet about their current situations. So the physical connectivity is lost, but the users are connected with the social media platform like Twitter, and they used to tweet about their current situation. So our task was to collect all the tweets which are appearing during the disaster situations, and then initially we filtered out the important tweets. Like we are not interested in the opinion related tweets. Okay, so we
Yes, ma'am.
simply
Yes.
discarded the tweets which contain some kind of emotion or sentiment. So so basically we only consider the tweets which contain neutral sentiment or the neutral emotion, because our hypothesis was that then that means those tweets are more informative. Then maybe those tweets contain some relevant information. So that way, in the initial stage only, we developed a classification framework which is which is basically classifying the tweet into two categories: informative and non-informative. And then the informative tweets are further processed for the summary system. Are you getting? So basically, Jyoti,
Yes,
my
ma'am.
point is that depending on your need, like if you want to if you want to select the sentences which contain some legal information, then maybe you have to accordingly define your objective function.
Objective. Yes,
So
ma'am.
you have to
Okay, ma'am.
match the
Thank you.
sentences with some terms which are related to legal documents, which are legally, legal terms. You have to see which
Yes, ma'am.
sentences contain maximum of those terms. So
Yes,
accordingly,
ma'am.
you can set priority to those sentences.
Okay, ma'am. Thank you. I got it.
So basically, these are the two types of summarization systems: extractive and the abstractive. As I mentioned, that extractive means we are simply selecting a subset of sentences for generating the summary, and the abstractive means that original set of sentences are somehow rephrased, and then we are generating some new sentences in the summary. These are the examples. You can see the extractive means we are selecting as it is the sentences, like the colored sentences is selected like this. You can see that brown color, blue color, purple color sentences are selected for generating the summary. But in case of abstractive, as it is the sentences are not selected. So we basically paraphrasing. We are writing the same thing but in a new style. So it is basically called the style transfer. So this is the abstractive. So abstractive is very difficult because it requires natural language generation. For a human being also, we face much difficulty. When suppose you have to rephrase something, suppose some document is given and somebody asks you to write the same thing in your own language, you will find difficulty. So basically abstractive summarization is very difficult. because it requires some human intelligence. We have to basically incorporate some human intelligence in the deep learning on the machine learning based systems. So there are different applications of summarization. One is this, one is called the query focused summarization. So query focused summarization means suppose a query is there, like suppose you are searching with the word Taj Mahal. If you search with the word Taj Mahal, you will get many documents. Now can we generate a summary out of those documents? Yeah, Srithan, yeah, I think, yeah, there are many summarization tools available, BART, Pegasus. Okay, these are the some tools available by Google. Basically, Google is working on this abstract summarization systems, and by Google, this Pegasus is developed by Google, and it is freely available, so you can use that. And BRT is also another abstract summarization system. So I was mentioning with the query focused summarization. So basically, this query focused summarization, as I mentioned, that you have a query, and you are searching with that particular query, and you are getting a set of documents, and now you can generate a summary out of the set of documents. Then if you are summarizing a single document, this is called a single document summarization. If you are summarizing multiple documents, then it is called the multi-document summarization. Then for figure summarization, so I think somebody was asking me some question with Python, which Python package support. So there is a demo session. Not today, but I think on 16th there is a demo session on summarization systems. There I will show you how to develop the summarization systems. So if we are considering the multiple documents, then basically that is called the multi-document summarization. Then there is a concept called the figurative summarization. So suppose there is a figure given, like if you see the biomedical articles. So the biomedical articles are full of figures. So figure caption is not sufficient to understand the figure, but the description of the figure is available in the paper. So maybe we can generate a summary of the figure considering the sentences in the particular article. This is called the figurative summarization. For example, in newspapers nowadays, figures play a very major role. So whenever reporters are writing an article, news article, he or she is also showing some images. So if you want to generate a summary of the image, considering the sentences present in the document, then this is called the figurative summarization. Then if you are summarizing a set of web pages, then it is called the web-based summarization. Sometimes maybe you can also generate summary of the set of emails. So suppose that you have received a set of emails and we are generating summary of that. Then this is called the email-based summarization. Then suppose we have information specific to a user's need and we want to generate summary out of that. Then this is called the personalized summarization. And suppose for example, in different blogs, users used to post different reviews of products or the movies. Okay, so suppose a new product has launched, or in any retail like in Amazon or Flipkart, users used to post the reviews of a particular product. So basically, maybe we can also these are the opinions about a particular product or a movie by the users. So we can also generate a summary of those opinions. So that is called the sentiment-based summarization. Then as I mentioned earlier, that we can also generate a summary out of the tweets. That is called the microblog summarization. So microblog summarization is very important nowadays because often users are posting about their current situation, or they are giving opinions on a particular event over Twitters. So we can also generate a summary from the tweets. So as I mentioned earlier, that summarization means that extractive summarization means you have to carefully select a subset of sentences. Now the selection of the subset of sentences means you have to define some objective functions. Basically, you have to assign some score to each of the sentences, and then you have to select some top scoring sentences. That is basically a kind of optimization problem, that you have to somehow score each of the sentences in the summary and each of the sentences in the document, and then the top scoring sentences should be selected. So there are different quality measures for summarization. like diversity. Diversity is one important factor because we do not want to have a summary where sentences are highly related. Like if the sentences convey the same thing, then that is not a good summary. We are expecting the sentences which are diverse in nature. The position of the sentence in the document is also important because in any document you can easily see that initial sentences are more important. The length of the sentence is also important. So basically you can see that length of the sentence is also important because you know that if the lengthy sentences are more informative compared to the shorter sentences. Readability should also be high, like when you will be reading the summary, the readability aspect should be high enough. Then coverage means we should be able to cover the entire theme of the document. And sentences in the summary should be coherent to each other. So like they should not be totally disjoint from each other. And sentence similarity with the title should also be high. So these are the different objective functions. And basically, either we can optimize only a single objective function at a time, or we can basically use multiple objective functions to simultaneously optimize by using a multi-objective optimization concept. And you can easily see that many of the objective functions are conflicting in nature. Like if you want to increase diversity, then readability will be compromised. If you want to increase the coverage, then also readability will be compromised. So many of the objective functions are also conflicting in nature. So as I mentioned earlier, that there are
Madam?
Yes, tell me.
But length of the sentence should be minimized, no? That means within minimized length of the sentence, our summary should be expressed, isn't it? Our objective is to summarize it. So
you can view it like that. No, I mean to say that when you will be selecting the sentences, in general, shorter length sentences are not preferred, no, because shorter length sentences are not informative. So if a sentence is having at least some threshold number, threshold length, then we can assume that this maybe that may contain some information. That was the motivation.
okay, one
there is
threshold value must be there.
Yeah, so there is a restriction in the summary length. So always if for the data sets that are available freely for the summarization systems, it is already mentioned that summary is of only 300 words or 250 words. So that check you have to do when you will be selecting the sentences. You have to stop when you reach that threshold. But here, this length of the sentence is to select the important sentences. So the idea is that shorter sentences are not important, but the longer sentences contain some relevant information.
Okay, ma'am.
Ma'am, I have a question.
Yeah, tell me. Yeah,
Ma'am,
please
am
go
I
ahead.
audible?
Yes, you are audible. Go ahead.
Yes, ma'am. Ma'am, these parameters are only for text summarization, or can they be applied to multimodal, say, audio summarization, that is speech summarization, which do not have a very good speech recognition tool where we can use the transcripts. So, will these parameters work for that kind of a scenario too?
That we have not tested. So basically, we have tested these parameters in the context of text summarization only, because when we are using the this multimodal summarization, also we have worked on multimodal summarization where we are considering the audio, video signals as well as the text signals. So there, basically, we have not used this kind of objective functions. So I will discuss the multimodal summarization if time permits. But mostly our observations are that these objective functions are good for text summarization. So for the audio setting, I am not sure whether these observations will provide similar result.
Okay. Thank you, ma'am.
Hello, ma'am. Hello.
Yes.
Hello.
Yeah, please go ahead. Yeah, I can hear you.
Okay, ma'am. About the length, if suppose some person is rephrasing, I mean, say you are saying that long length give more information. Suppose if I rephrase that particular sentence into a shorter phrase, okay, can we calculate the weight for that instead of length?
Yeah. Basically, you are talking about this abstractive summarization. So basically, I am not here.
It gives the more information.
True. Very true. Very true. Yeah. Basically, that is the calling the paraphrasing. Like in case of abstractive summarization, the idea is to merge 2-3 sentences into a single sentence. Okay. In case of abstractive summarization, if you see the model used behind Pegasus or BART, so first of all, they are selecting the important sentences, and then they are somehow, combining these sentences into some single sentences. Okay. So what you are saying is basically the idea behind abstractive summarization, but in case of extractive summarization, there is no scope. There is no scope of changing the sentences. So we have to simply select the sentences from the original document, and sentences will be kept as it is in the summary.
Okay, got it. Thank you, ma'am.
Yeah. So I think there is one more question. So can we have the question answer session? Yeah, true. Radhika, yes. So maybe later we should take the question answer at the end. Maybe last 15 minutes we can discuss different questions and I can provide all the answers. Yeah. So basically these are different quality measures for summarization. And as I mentioned that we can either optimize a single objective function or multiple objective functions simultaneously by using multi-objective optimization concept. So there are more different types of summarization systems, like as I mentioned that query focused I have already mentioned, and then summarization systems can be supervised or unsupervised. If you know the machine learning techniques, so there are two different paradigms of machine learning: supervised and unsupervised. So in case of supervised, basically we need training data. So we need to train the model using the training data. So here training data means in the input side there are documents, and in the output there is a summary. So the system will be trained using this kind of parallel corpus, where in the input we have document, original document, and in the output we will be having a summary. Then we can also have the monolingual, multilingual, or the cross-lingual summarization. All the documents of a particular of the corpus are written in a single language, then this is called the monolingual. But if suppose that we have a collection of we are also working on a corpus where documents are written in multiple languages, then this is called the multilingual. Or if suppose in a document only there is a switch between two languages, then this is called the cross-lingual. So the rest I have already discussed, that if we are summarizing a set of web pages, then this is called the web-based summarization. If we are summarizing the set of emails, then this is called the email-based summarization. If we are summarizing the information specific to a user's need, then this is called the personalized summarization. And if you are summarizing the opinions, then it is called the sentiment-based summarization. So there are many existing techniques for the summarization, and we did a thorough literature survey. Many of the techniques are based on supervised techniques, some are based on unsupervised techniques. So we are mostly, we are following some unsupervised approach, because generating a label data is very difficult in case of summarization, because you can easily understand that training data means in the input side there will be documents, and in the output side there will be summary. And it's very difficult, manually generating summaries for multiple documents and then using this training data to train a system would be very difficult. That's why basically here we develop some unsupervised based approaches for solving the summarization problem. So what do we mean by unsupervised based approach? Basically here we have used the clustering based approach. So there are two stages in our proposed approach. In the first stage, we are simply applying the clustering on the sentences. So we have basically extracted all the unique sentences from the document, and then we are applying clustering on the sentences. and that will give us the sentence clusters. And then finally, from each cluster, we will be selecting the important sentences to generate the summary. So the idea is that first of all, we have to group the sentences which convey the same information, and they should be put into a single cluster. And then from different clusters, we have to select one sentence or one or two sentences to generate the summary. So here, our literature survey concludes that there are several extractive single document summarization algorithms, and these existing systems are basically unable to automatically detect the number of clusters. So when we are generating the sentence clusters, how many clusters will be there? That is a kind of a unknown, it is very difficult to understand how many optimal clusters are there. And none of the existing document summarization captures the semantic similarity present in the sentences. And they also suffer from the low convergence rate and the low score. So we have formulated the summarization problem in the framework of single objective optimization. What is the solution to the drawback? So we need to develop an automatic text summarization system using multi-objective optimization, which is called the sentence clustering. So this is a two-stage approach. In the first stage, we are basically forming the sentence clusters, and then from each cluster, we are selecting some important sentences to generate the summary. So basically, it is a two-stage approach. In the first stage, we are generating the sentence clusters, and then in the second stage, some important sentences from each cluster are selected to generate the summary. So our proposed system is capable of automatically determining the number of clusters automatically. So in how many clusters the sentences will be divided, that is what basically automatically determined. And we also make use of several sentence coding features to select the sentences. So first is the sentence clustering. So we have basically developed a multi-objective optimization based approach for sentence clustering. And once we have the sentence clusters, next is to assign some scores to different sentences of a particular cluster. And then we select some the sentences which are having high scores from each cluster to generate the summary. So we make use of several sentence scoring features to select the sentences, and we are able to achieve better root score in comparison to state-of-the-art technique. Here, first of all, we are generating the as I mentioned that this is the overall steps of the proposed approach. So we are first performing the sentence clustering. Then we are ranking the clusters. Then we are extracting sentences from top rank clusters using some sentence coding features until we get desirable length of the summary. So multiple cluster quality measures capturing different data properties are required to be optimized simultaneously. So basically, we are first performing the sentence clustering. We are ranking the clusters, and then we are extracting sentences from top rank clusters using some sentence coding features until we get desirable length of the summary. So these are the steps of the proposed approach. So here, when we are doing the clustering, you know that these are the basically the sentence clustering. So how to measure the similarity or the dissimilarity between two sentences? Because somehow in the semantic space, we have to measure the similarity or the dissimilarity. So for measuring the similarity or the dissimilarity between two sentences, we have used the word over distance. This distance is basically a kind of semantic similarity measure. So first we have to generate the embeddings. You may aware of the word to vec. So by using the word to vec, we can generate the embeddings from the different words of a particular sentence. Suppose there are two sentences. Obama speaks to the media in Illinois, and there is another sentence, the president greets the press in Chicago. So these are the two sentences. And now we can easily get the word embeddings of the individual words. So for Obama, we can get an embedding, speaks, we can get an embedding. So this way we can generate embeddings for individual words. Next, we can basically map, like Obama can, now we have to map each word to the nearby word. Like Wama can be mapped to president, Speaks can be mapped to grid, Chicago can be mapped to Illinois, media can be mapped to press. So this way we are basically making a mapping, and then the similarity, these distances can be summed up, and then that would be the word over distance between these two sentences. So if two sentences are similar, then the WMD would be equal to 0. Otherwise, there will be positive WMD, which will denote the similarity between the two sentences. So word over distance is the amount of distance that the embedded words of one text needs to travel to reach the embedded words of another text. So it basically makes use of the word embedding. So if two sentences are similar, then the word WMD would be equal to 0. Otherwise, there will be a positive value of the WMD. But WMD will basically give us the distance between two sentences. It is basically the semantic distance. So for solving the summarization problem, or basically for generating the sentence clusters, we have used a multi-objective optimization based clustering technique. So, in general, for solving the multi-objective optimization problem, evolutionary algorithms are very popular. So, evolutionary algorithms, there are different types of evolutionary algorithms available: genetic algorithm, differential evolution, etc. So, either we can use the evolutionary algorithms, or we can use the swarm optimization techniques. Particle swarm optimization, Gray-Wood optimization, water cycle algorithms. These are different swarm optimization techniques. Evolutionary algorithms are inspired by the biological phenomena. So here a solution is called an individual. Representation of a solution is called the chromosome. Components of the solution are called the genes. Set of solutions are called the population. Survival of the fittest is called the Darwin's theory. Search operators are the crossover and mutation. And the iterative procedure is called the generations. So evolutionary algorithms are basically inspired by the biological phenomena, and they have these different components. Here a solution is called an individual. Representation of the solution is called the chromosome. Components of the solution are called the genes. Set of solutions are called the population. Survival of the fittest is called the Darwin's theory. So this way, there is a, we can easily map the concepts with our biological phenomena. So this is the flow of the evolutionary algorithms. Basically, there is an initial population. So initial population is nothing but it is a set of chromosomes, and each chromosome is a basically possible solution. So here in our case, our solution is basically a clustering solution. So each solution basically defines a way of partitioning the sentences into multiple clusters. So the population is consisting of multiple solutions, and each solution is basically a way of partitioning the sentences into multiple clusters. Then we are computing the fitness values of the individual chromosomes of the solution, and we have to operate for Gmax number of iterations. So Gmax is the maximum number of generations, and then we have to generate the new solutions by using the mutation and the crossover operations. We have to compute the fitness values. We have to update the population, and these steps have to be updated, have to be repeated for maximum number of generations. So you can see that this is a loop. So new solutions are generated by using the mutation and the crossover operations. Then their fitness values mean that their objective function values are computed, and then we are updating the population. So the new solutions and the old solutions are combined, and the base set of solutions are used to update the population. So this is a kind of a loop, and this loop is continued up to Gmax number of times. So Gmax is the maximum number of generations. And finally, we get a set of parallel solutions on the parallel surface. Find a set of solutions as diverse as possible. So here, as the evolutionary algorithm, we have used the differential evolution. So differential evolution is also an evolutionary algorithm. So it maintains a population of candidate solutions. And there are two genetic operators, crossover and the mutation. By using the crossover and the mutation operations, we are generating a set of candidate solutions. Then the candidate solutions are combined with the old solutions. And finally, we are applying the selection operation to select the best set of solutions for the next population. This is the flow of the differential evolution. Okay, choosing the target vector. We are randomly choosing two population members. We are building a weighted difference vector. We are adding a third randomly chosen vector. We are performing the crossover with the target vector to get the trial vector. Smaller cost value survives into the next generation. This is our problem statement. As you know, already understood that here it is a two-stage problem. So summarization, the extractive single document summarization is basically solved using two stages. In the first stage, we are basically clustering the sentences. So suppose we have SK number of sentences. So this SK number of sentences are clustered into some basically those are grouped into multiple clusters. And so that we can see that summation over all the sentences are divided, sentences are distributed in multiple clusters. Now the union of all the sentences which belong to multiple clusters should be equal to total number of sentences, and the intersection should be equal to phi, because here we have considered the crisp clustering, not the fuzzy clustering. So there will be no overlap between the clusters. So like a particular sentence can only belong to a single cluster. So we have not assumed that if a sentence can also belong to multiple clusters. This way we are dividing the set of sentences into multiple groups, and so that the union of all the clusters equal to the number of sentences, and the intersection of two clusters equal to phi. And in the process, several cluster validity indices are basically optimized simultaneously. So val1, val2, val_m are different objective for different cluster validity indices, and our objective function is to simultaneously optimize these cluster validity indices. So here we have developed three algorithms. Basically, one is based on differential evolution, second one is based on the water cycle algorithm, and third one is based on the Gray-Wolf optimizer. Basically, our underlying optimization framework is very remains same. Only the optimization technique is different. So either we are using differential evolution or the water cycle algorithm or the Gray-Wolf optimization to simultaneously optimize multiple objective functions. So here, what are the key points of the proposed algorithm? So we have used a semantic-based schema to represent a sentence in the form of a vector. Now to determine the similarity or dissimilarity between two sentences, word over distance is used. So word over distance basically utilizes the what to pick model. So based on the what to pick model, we can easily calculate the similarity or the between two sentences. Then a multi-objective clustering technique is developed to cluster the sentences present in a document. So for generating the clusters, in the multi-objective clustering framework, two well-known cluster validity indices are optimized simultaneously, and this multi-objective clustering technique is capable of automatic determination of the number of sentence clusters. And finally, once we have the sentence clusters, now we can basically assign some assign some score to all the sentences in a particular cluster, and that way basically we can rank the clusters which are in a particular we can rank the basically sentences which are in a particular cluster, and then we can select the top ranked sentences from each cluster. So this is the basically key features. That one is that now we are using this word over distance, which is basically a semantic similarity measure, and our proposed algorithm is capable of automatically determining the number of clusters. So how many sentence clusters are there, that is automatically determined, and in the process we are simultaneously optimizing multiple cluster validity indices. This is the overall flowchart of the proposed approach. Differential evolution is used as the underlying optimization technique, and self-organizing map is used as a reproduction operation used to generate good quality solutions. So you can see that there is suppose a single document. We are doing some pre-processing. We are initializing a population. So population is consisting of multiple chromosomes. So then we are checking whether generation has reached Gmax or not. There is a self-organizing map training. So this self-organizing map is basically used to determine the nearby solution. So given a particular solution, which are the nearby solutions in the objective space. So that is basically calculated by using the SOM training. Once we get the neighborhood of a particular solution, then this neighborhood is basically used to generate the matching pool. So you can easily understand that there is a solution. Now we can easily get the neighborhood of a particular solution by using the self-organizing map. So this neighborhood is basically obtained by using the in the objective space. And then solutions in the solutions which are in a neighborhood, basically they constitute the matching pool, and then we apply the crossover and the mutation operations based on the matching pool, and that way generating the new population P dash. We are merging P and P dash together, and then we are selecting the best mod P number of solutions, and we are updating the SOM training data. So this is a loop you can see, and this loop is executed for Gmax number of times. So Gmax is the maximum value of number of generations. So this loop is executed for Gmax number of times. At the end, we will get a set of solutions on the final paratoptimal front, and we will generate a summary for each of the solutions, and basically we will select the best one. So you can see that for representing the solution, somehow we have to represent the clustering solution in the form of a string or in the form of a chromosome. So here we have used the center-based encoding. So the centers of the individual clusters are encoded in the form of a chromosome. So for example, here we have assumed that there are 4 centers. So this X1, X2, X3, X4, they represent 4 centers, and each center is having some dimensions you can see. So basically here we have used the center-based encoding. So a chromosome is basically a collection of cluster centers. So each center is basically a collection of some feature values. So number of cluster centers is varied over a range. So 1 to n is the total number of sentences in the document. So each solution has varied number of clusters between 1 to n, where n is the total number of sentences in the document. And each solution is having 2 objective functions, PVM index and the Zybani index. These are 2 cluster validity indices. So these 2 validity indices basically can capture the cluster quality. So how good the clusters are. So those could be measured by these cluster validity indices. Because as you know that accuracy, F measure, precision, recall, those are the metric values for classification systems. But for in case of clustering, those metrics are not popularly used. So in case of clustering, we are using cluster validity measures. So PVM index, Zybani index are 2 popularly used cluster validity indices, and those are simultaneously optimized by using the search probability of multi-objective optimization. So these are basically we have used the genetic operators, matching pool construction, and the crossover and mutation operations. So matching pool is constructed. So matching pool is constructed after considering the neighborhood solutions of the current solution, retrieve using self-organizing map. So you know self-organizing map is basically a unsupervised neural network. It is so what it does is basically it basically maps the higher dimensional data into 2-dimensional space in a grid-like structure, but preserving the neighborhood property. Like in the higher dimensional space, if 2 solutions are nearby, then in lower dimensional space also those 2 solutions will be nearby. So basically it basically captures the neighborhood property, and basically by using the self-organizing map is mostly used for data visualization. So because you cannot visualize the high dimensional data, but by using the self-organizing map, we can easily map the high dimensional data into a lower dimensional space, and then we can easily find out the neighborhood of a particular solution. So you can see that if the current solution is H, then all these white solutions are in the neighborhood. So these neighborhood solutions can be used to generate the matching pool, and then we can select some random solutions from the matching pool to generate the crossover and the mutation operations. Matching pool is constructed after considering the neighborhood solutions of the current solution retrieved using self-organizing map. Only neighboring solutions can mate to generate the new solutions. So what is the crossover operation? So you can see that this is the crossover operation, which is very standard for the differential evolution. Two solutions are randomly selected from the matching pool, and then if the random number is greater than the crossover probability, then we are generating the we are applying this operation y dash I equal to xi current plus f into xi1 minus xi2. Otherwise, y equal to xi current. Rand is the random probability lying between 0 to 1. CR is the crossover probability. And then after this crossover operation, if suppose the values are out of the range, like if the yi dash is less than xil, or if the yi dash is greater than xiu, then basically, we have to repair the solution. We have to make the solutions inside the range. So mutation operation, there are three types of mutation operations. So you know that either we can increase the number of cluster centers by, either we can increase the number of clusters by 1, or we can decrease the number of clusters by 1. So because we are having varied number of cluster centers in each solution, as I mentioned during the chromosome initialization. So you can see that each because number of cluster centers are also automatically determined. So for each solution, we have selected a random number between 1 to n, and those many cluster centers are encoded in a particular solution. So that's why that during the mutation operation, we are either increasing the number of cluster centers in a solution, or we are decreasing the number of cluster centers in a solution. So after repairing the solutions generated by the crossover operation, we have applied the concept of polynomial mutation, which generates highly diverse solution. And also there are two different types of mutation operations. Either we can increase the number of clusters present in a solution by 1, or we can delete the number of we can decrease the number of clusters for the right solution by 1. And next is the selection operations. For the selection operation, the new solutions and the old solutions are combined. And basically, suppose there are newly generated n number of solutions in the new population P dash. The old population P contains n number of solutions. So this P and P dash are combined together. That will give us 2n number of solutions. Now out of these 2n solutions, you have to select the best n solutions. So for that, we are applying the non-dominated sorting and the crowding distance. So we are dividing the solutions into different, different paratoptimal surfaces. So you can see like these are the paratoptimal surface 1, which contains all the rank 1 solutions. So if you see solution A and solution B, they are non-dominated to each other, and basically they are non-dominated to each other, and they are also not dominated by any other solutions. So if you see there are two objective functions f1 and f2, we are maximizing both the objective functions. And solution A and solution B are non-dominated to each other, and they are also not dominated by any other solutions. So basically they constitute the paratoptimal surface 1 or the rank 1 solutions. Then C and D are also non-dominated to each other, but they are dominated by either A or B. So that's why they basically form the rank 2 set of solutions. This is called the paratoptimal surface 2. And E and F, they are also non-dominated to each other, but they are dominated by C or D or A and B. So basically that's why they are paratoptimal surface 3. So first of all, we have to divide the solutions, this 12 number of solutions, into different paratoptimal surfaces. We will start from paratoptimal from the rank 1 solutions. So we will, for the new generation, for generating the population for the new generation, we will basically start from the paratoptimal from the rank 1 solutions. We'll copy all the solutions in the rank 1 solutions in the new population, and this way then we will go to the rank 2 solutions. But suppose we are not able to accommodate all the solutions of a particular rank in the new population. In that case, we have to use the non crowding distance concept. So basically, crowding distance means that we have to compute the crowding distance, what is the distance from a particular solution from the two neighbors. If the distance is high, then the solution will be selected. So basically, the idea is to select those solutions which are in a less crowded region. So if the solution is in a less crowded region, that is more important than the solution which is in a high crowded region. So because another objective of multi-object optimization is to increase the diversity. So we want to basically generate solutions over the apparent optimal front. So that's why this non-crowding distance concept is introduced. So this is the first stage of our proposed approach. After applying this differential evaluation based clustering technique, we'll be generating sentence clusters. So basically, each solution in the parallel front will be basically a kind of clustering. It will basically group the sentences into multiple clusters. Now, basically, the next stage is how to select the important sentences from each cluster, because now sentences are somehow grouped together based on their semantic similarity. Now, it is important to select important sentences from each cluster. So, at the end of the optimization algorithm, set of solutions are obtained. So, basically, now to generate the summary, what we are doing, we are first computing the document center. So, document center is that particular sentence whose average distance to all the other sentences is the minimum. So, suppose you know that the document center is that particular sentence whose average distance to all the other sentences is the minimum. And then basically clusters present in the ith solution are ranked. Like you can see that suppose CK is a particular cluster center and SM is basically, you know, that SM is the document center. So we are computing the word buffer distance between the cluster center and the document center. So then we are ranking. Okay, so the clusters are also ranked. So based on this distance, clusters are ranked. So basically, finally, clusters are ranked in descending order based on this ZK scores. This ZK is the distance between the cluster centers and the document center. The clusters are ranked in descending order based on this ZK scores. And finally, a cluster is having multiple sentences, and each sentence in the cluster is basically, you can see that we have assigned some score based on these four objective functions. One is the length of the sentence, which is the F1, position of the sentence in the document, similarity with the title, and the anti-redundancy. So these are the four objective functions. So our target is to increase the length of the sentence, position of the sentence in the document also we want to increase, similarity with the title also we want to maximize, anti-redundancy we want to minimize. So basically each sentence is assigned a score which is the weighted weighted combination of these four factors. So there are four factors, F1, F2, F3, F4, and alpha, beta, gamma, delta are the weights. So we are computing the weighted combination of these four factors, and that is basically denoting the sentence score. So we arrange sentences in descending order present in a cluster according to the sentence scores. Now to generate summary, clusters are considered rank-wise. Given a cluster, top rank sentences are extracted sequentially until summary length reaches to some threshold. So basically as I mentioned earlier, the sentences are first the clusters are ranked, and then in a cluster there are many sentences. So all the sentences in a cluster are also ranked, and we select the top ranked sentence from each cluster to generate the final summary. So for evaluating this particular, our proposed approach, we have used two data set, which is called the DUC 2001 and DUC 2002. So this is the document understanding conference. In this particular conference, two datasets are released for summarization purpose. So you can see in DUC 2001, there are 30 topics. In DUC 2002, there are 59 topics. And number of documents in DUC 2001 is 309. Number of documents in DUC 2002 is 567. And length of the summary is always 100 words. So for as I mentioned that basically in order to compare, like whether our suppose our algorithm is producing a summary, whether that summary is good or bad, in order to evaluate the developed summary, we need to have some metric. Like that accuracy, F measure, recall, these are the metrics for the classification systems. We also need a metric to evaluate the summarization quality. So RUSE is basically a very popularly used metric for evaluating the quality of the summarization system. So here you can see that n represents the length of n-gram. So how many n-gram means how many consecutive words we are matching. So count match n-gram is the maximum number of overlapping n-grams between reference summary and the system summary. Count n-gram is the total number of n-grams in the reference summary. In our experiment, n takes the values 1 and 2. So basically either we can match 1 gram individual word by word we can match, or we can match consecutive 2 words. That is called a bigram. So basically we can have RUSE 1 or the RUSE 2 values. So either we can map individual words or we can map bigrams. So they basically RUSE is a very popular metric to check the quality of a particular summary. So as I mentioned, we have proposed 3 approaches. One is based on differential evaluation, second is based on Gray-Wolf optimization, third is based on the water cycle algorithm. And we are comparing with different existing systems. And you can see the RUSE 2 and the RUSE 1 values. So RUSE 2 scores of the differential evaluation based systems is the highest, and also for the DUC 2002 also MOD performs much better compared to the existing systems. So these are some examples of the good summaries. You can see in most of the cases there is a matching. This is the actual summary, predicted summary, and in most of the cases there is a matching with the actual summary. So this is an example of a bad matching, but poor summary where there is not much match. So and these are the parameters of the proposed approach. And these examples show that yes, indeed, you can see these are our rank one solutions. So after the final execution, we are getting many rank one solutions. This means that indeed there are different ways of summarizing the particular document. So each solution basically represents a particular way of clustering the sentences. So you can see there are different possibilities of clustering the set of sentences. This is one approach, and you can see for further details you can read this our paper, which is accepted in this knowledge-based systems journal. So the title of the paper is basically extractive single document summarization using multi-object optimization, exploring self-organized differential evaluation, Gray-Wolf optimization, and the water cycle algorithm. So you can see the details of this particular work in this particular paper. Now I will show you another approach where we have used a binary optimization framework. So in the previous approach, it was a 2-stage framework. In the first stage, we are performing the sentence clustering. In the second stage, from each cluster, we are selecting the important sentences. So we are assigning some score to individual sentences based on some sentence scoring features. And then we are selecting the important sentences from each cluster to generate the final summary. That was the proposed approach. But in this particular approach, it is a single stage approach. Here, it is a binary optimization approach. Here, either a sentence will be selected or it will not be selected. So basically, it is a binary optimization technique. And here again, we have used the differential evaluation. But now, as this is not a clustering based approach, so we are directly optimizing different objective functions. So as I mentioned earlier, that there are different objective functions. In order to select important sentences to generate the summary, we can have multiple objective functions like sentence position plays a very important role. Sentence similarity with the title is also a very important aspect. Coverage, so you have to select all the sentences which can easily cover the entire document. The sentences in the summary should be coherent to each other. Sentence length should be high enough. Readability aspect should also be improved. So these are the different objective functions, and our task is to basically simultaneously optimize them. So in this particular work, we have basically simultaneously optimized this objective functions by using the multi-object optimization concept. So the text document is having multiple sentences. And we are selecting only a subset of sentences for generating the summary. So you can see that if you see the existing literature, then most of the, as I mentioned earlier also, most of the summarization systems, there is a question, but maybe I can take the question again. Yes, so madam, is there any factor about the distances between two sentences to find the relation between them? Yeah, I will discuss. So basically this word mover distance, as I mentioned, that word mover distance can be used to see the similarity between two sentences. So the word mover distance, if it is equal to 0, that means the two sentences have the same semantic content. So it is a semantic similarity measure, not the syntactic similarity measure. For the syntactic similarity, we can use the TF-IDF based vector representation. So each sentence can be represented by the TF-IDF vector, and then we can easily compute the cosine similarity. So basically, we have formulated the summarization problem in the framework of single objective optimization. So in the existing framework, mostly people are using single objective optimization framework. They are optimizing only a single objective function, and none of the existing single document summarization techniques captures the semantic similarity present in the sentences. So we are the first to basically use the multi-objective optimization concept. And as I mentioned, that we are using the semantic similarity measure, which is the word mover distance, to capture the semantic similarity present in the sentences. So these are the basically the objective functions that we have used. So one is the sentence position. So it assigns higher scores to the initial sentences of the document. As the sentence position in the document increases, the value of P decreases. Second is the similarity with the title. So it measures the similarity with the titles. We are maximizing this. Third is the coverage. It measures the extent to which sentences in the summary provide useful information about the document. Fourth is the length of the sentences. It favors the longest sentence but does not entirely rule out the medium length sentence. In cohesion, it measures the relatedness of the sentences that make up the summary, or it recognizes whether the summary sentences are discussing about the same information or not. And readability, it measures the readability of the summary. So this is the overall architecture of our proposed approach, or a flowchart of our proposed approach. So we have, there is an input is the single document. We are applying some pre-processing. We are filtering out the important sentences. Then there is a population initialization and the objective function calculation. Then we are checking whether we have reached the maximum number of generations or not. So what we are doing is that we are generating the, there is self-organizing map. The self-organizing map is used to find out the neighborhood, as I discussed before. The self-organizing map is used to determine the neighborhood of a particular solution. And this neighborhood is basically used as a matching pool. So based on the matching pool, we apply genetic operators to form a new population P dash and calculate the values of the objective functions. We merge P and P dash together, and then we apply non-dimensional sorting and the crowding distance to select the best P mod P number of solutions. We update the sum training data, and this is a loop you can see. So this loop is executed for maximum number of generations. And at the end of this loop, when the maximum number of generations is reached, we get a set of solutions on the parallel surface, and we can select a single base solution, and we can generate a summary. So this is the overall flow chart. What is the question? So please explain the input and output of each process in the flowchart with respect to a document. Okay, so you can see that here the input is a document. So after pre-processing, you will be basically getting a set of sentences, unique sentences present in a particular document. And then population initialization is basically, I will show you that each chromosome or each solution is basically a binary representation. So the length of the solution is equal to number of unique sentences present in the document. So suppose the document is having 1000 sentence, then the chromosome is of length 1000. So a particular entry, it represents 0 means that the sentence will not be selected, and the entry equal to 1 means the sentence will be selected. This is a binary representation, and the population is basically consisting of multiple binary chromosomes. And we have to compute the objective function values of each chromosome. Now we are checking whether G is less than G max or not. So basically, there is a self-organizing map training. So basically, that we are generating the training. We are training the self-organizing map just to identify the neighborhood of a particular solution. And then genetic operators are basically the standard mutation and the crossover operators of differential evolution, especially binary differential evolution. With the binary differential evolution is having some crossover and the mutation operations. So that we are applying to generate the new population P dash. So these are the steps of the binary differential evolution. Okay, here we are not using the sentences. So basically these are the steps of the binary differential evolution. But when we are computing the objective function, so the solution will tell you which sentences are selected for the final summary. So accordingly, as I mentioned earlier in the previous slides, so you can compute these objective functions. You can compute the coverage by finding out the similarity between two sentences. Here similarity is the word mover similarity. Then you can compute the length of the sentences by using this formula. We can compute the cohesion by using this formula, readability by using this formula. So basically, that for objective function calculations, we have to compute we have to basically use the sentence similarity values. So then we are merging P and P dash together. And as I mentioned that now we have to apply the non-dominated sorting and the crowding distance. And we have to select the best P number of solutions. This process will be repeated. So ultimately here, what we will be getting, so ultimately at the end of the execution, we'll be getting a set of solutions on the paratoptimal front. So now each solution is basically a way of, basically each solution is a binary partitioning of the sentences. So the sentences which will be selected for generating summary will have the value equal to 1. So those sentences will be selected and they will basically form a summary. Here there are two approaches that we have used. In the approach 1, we have added some weight factor to individual objectives. So we have 6 objectives I discussed earlier. So each objective is having a weight factor, alpha, beta, gamma, delta. So these are the weight values. All the objective function values are multiplied with their respective weights and then simultaneously optimized. And in approach 2, all the objective function values are simultaneously optimized, no weightage is assigned. Then there are different versions as well. Either we are using an approach with sum or without sum. And different distance functions are also used. Like either we can use the cosine similarity or the normalized Google distance or the word mover distance. So these are the results. You can see that these are the, it is not possible to, there are 6 objective functions. It is not possible to visualize the, the 6-dimensional space. So basically, we are simply mapping them in a 3-dimensional space, and then we are visualizing. Like here, the 3 objective functions are coverage, readability, sentence position, and we can easily visualize that there are multiple solutions on the paratoptimal surface. So these are the results. You can see that approach 1 uses the normalized Google distance, and again we are using the cosine similarity or the WMD distance, and with sum and without sum. And the same data sets are used, DUC 2001 and the DUC 2002, and RUS 2 and the RUS 1 score values. And you can see that approach 1, basically in most of the cases, our proposed approach attains much higher values compared to the existing systems. So these are all the existing systems. So yeah, so basically this work is accepted in clause 1. So as you understand that here the main novelty was that we have not used this two-stage approach, but we have used the binary differential evolution, and either a sentence will be selected or not selected. And by using the search capability of binary differential evolution and by simultaneously optimizing the 6 objective functions, we are basically selecting the best set of solutions. So let me just quickly go through another approach, and then maybe we can start taking the questions. So one is basically the figurative summarization. So the figurative summarization, as I mentioned, figurative summarization means that suppose in a particular document there is a figure, and you want to generate the summary of the figure. So now input statement is different. So till now you are considering a document as an input, and then you are generating a summary of the document. But now the input is the document as well as a figure, and given the document, we have to generate the summary of the figure. This is the problem statement. So we have to develop an unsupervised system for automatic summarization of figures in the biomedical articles. So there are many figures and there are many sentences. We have to generate a summary of different figures. So this is a sample figure in a biomedical article. So you can see, suppose if you see the caption, by seeing the caption, you will not be able to understand the figure. So in this case, basically, we have to go through the entire document to understand or to interpret the figure. The figures are always difficult to interpret by humans as well as machines. According to Foottrail, 50% of the text in the biomedical articles are related to figures only. Therefore, associated text in the article can be used to describe them. So here again, we are using the binary optimization. So you can see our chromosome of the solution. So our chromosome of the solution is basically a binary string. So our chromosome of the solution is a binary string. So here 1 and 0 represents whether the sentence will be selected or not selected. So 1 denotes that the sentence will be selected, and 0 denotes the sentence will not be selected. So for example, here you can see that the first, fourth, fifth, and eighth sentences are selected, and the second, third, sixth, seventh, and ninth, and 10th sentences are not selected. So this is a binary representation. So it is a binary differential evolution framework utilized as the underlying optimization strategy. There are many sentences in the biomedical article. It is difficult to find the relevant sentences summarizing a particular figure. So we are simultaneously optimizing multiple objective functions. For language representation, BioBart model is basically used. So basically, you can here we have used the differential evolution as the underlying optimization technique, and different variations of the differential evolution are used. And we have also used different values of CR and F parameters. These are 2 parameters of the differential evolution, and these are our objective functions. So first is the first objective function measures the cosine similarity between sentences in the summary. So which we try to minimize because we want to maximize the diversity. Second basically measures the anti-redundancy between sentences of the summary in terms of textual entailment relationships. Then third basically calculates the number of entailed sentences in the summary to the figure's caption. So these are the different objective functions that we have used. And these objective functions are basically related to diversity and the coverage or the anti-redundancy of the sentences in the summary. So basically this is you can see this is again the proposed flowchart. So here the input is the figure and the caption and the sentences of the article. We have to pre-process the sentences, like we have to remove the stop words. We have to generate the embeddings of the individual words. That is the pre-processing. Then we are initializing the population randomly. And then we are calculating the objective functions. Then you can see we are checking whether generation has reached the Gmax or not. If yes, if not, then we are generating new solutions to generate the new population P dash. We are calculating the objective function values of P dash. We are merging P and P dash together. Then we are applying non-dominator sorting. We are selecting the best piece number of solutions. And then finally, when we reach the maximum number of generations, we select the best solution and report the corresponding summary. So here we have used two datasets, FigSum GS1 and FigSum GS2. These datasets are available online here from this particular site, and these are freely available. You can also download them. FigSum GS1 is having 91 figures and the corresponding summaries, and FigSum GS2 is having 84 figures and the corresponding summaries. Actual and goal summary are also available by the annotators. So these are the parameters used. And you can see that we did a ablation study. We have varied the different combinations of the objective functions. And you can see when we are using these 4 objective functions, we are getting the better results. So yeah, so this is this is one example. This is the actual summary and the predicted summary. And these are the parallel surface. We can see that there are many solutions of the parallel surface. So we also did some error analysis. So sometimes there is a nested captioning, like caption of one figure is referring to the other figures. So in that case, our proposed approach will not be able to identify the correct summary. The captions of some figures refer to captions of other figures of the same article. Sometimes captions are very brief. They contain only 3 or 2 words, which are insufficient to explain a figure. So I think I should stop now and I should take some questions. So basically, for more details, you please see publications. So I have already shown you that these are the publications related to, like, in recent years we are exploring the summarization problems and we are developing different unsupervised approaches for solving the summarization problems. So there is also a demo session on 16th, and on 16th I will be discussing about the multimodal summarization systems, and then we will also show you how to develop a multi-objective optimization based summarization system. So now, if you have any questions, you can take them.
Hello, ma'am.
Yes, please go ahead.
On PPT number 30, just actually I explained
30?
that 30, yeah.
Yeah.
Actually, you have explained about that similarity index nearby in high dimension and low dimensions are same. Actually, I have not understand that statement here.
Okay, yeah. So basically, self-organizing map, if you read the theory of self-organizing map is basically unsupervised neural network, okay? So like neural network is basically a classification technique, but self-organizing map is basically unsupervised neural network. So what it does is that, suppose you have a multidimensional data, so it will basically map the multidimensional data in a 2-dimensional grid. Like you can see, it's a grid-like structure, no? This is an array, 2D array. So there are some rows and there are some columns. So basically the multi-dimensional data will be mapped to this 2D grid. Okay. So so that the neighborhood property is basically preserved. So suppose in the multi-dimensional space, you have a point P1 and P1's neighbors are P2, P3, P4. Then when you will be mapping them, like it is basically feature selection. So it is basically a kind of, a subset selection, like, the principal component analysis or the linear discriminant analysis. It also projects the data in a lower dimensional space. So from the higher dimensional space, it is basically projecting the data in a lower dimensional space. But in a lower dimensional space also, the neighborhood property is basically neighborhood basically preserved. Like if in the original space P1 is having neighbors P2, P3, P4, then in the reduced space also P1's neighbors should be P2, P3, P4.
Means like eigenvalue, if you calculate then and then we go to the lower rank like that only.
No, that is not, no, it is not principal component analysis uses the eigenvalues, eigenvectors. It doesn't utilize the eigenvalues and eigenvectors. it basically, it basically calculates the distance from the solution to the neighbors.
Okay. Okay. Thank you, ma'am.
Yes.
How did you use work to make here that in the diagram you have shown that the nearer in the context nearer words you have shown?
Yes, very true. Yes.
Here,
So
here.
what to make? Yeah. So what to make is a tool. Maybe in the demo class we can show you. So
Yeah,
what to make is a deep learning tool.
Yeah. So here you got this Obama and president from that document itself with your what to make model.
No, I got the vector representations of Obama from the what to make. So Obama speaks to the media in Illinois is one sentence, and the other sentence is the president greets the press in Chicago. Okay, these are the two sentences. So my task is to find out the semantic similarity between these two sentences.
So you must have modeled this feature space, means features you must have extracted.
No, I have just used the what to make model. So I have applied what to make on Obama. I got a vector representation. I also apply the same what to make model on president. I got a vector representation. And then we find out the cosine similarity between all possible pairs. Like for Obama, I have a vector, speaks is having a vector, to is having another vector, the is having another vector, media is having another vector. So all the words in sentence 1 are having their vector representations. All the words in sentence 2 are also having their vector representations. Now, if suppose sentence 1 is having n number of words and the sentence 2 is having m number of words, then you have to compute n into m number of pairs. Okay. So you have to consider all the pairs and you have to calculate the cosine similarity between all the pairs. And then basically the word will be mapped to the word with respect to which it is having the minimum cosine similarity. Oh, sorry, maximum cosine similarity.
Maximum, yeah.
Yeah. So this way, this mapping is basically done.
And one move distance that you have mentioned means what is that actual concept?
What is there? Where?
Move distance. This mover distance you have considered. Mover, why you call it mover distance?
Oh, mover means because we are basically this is the concept is like this: amount of distance that the embedded words of one text needs to travel to reach the embedded words of another text. Okay.
Path
So
length it is. It means it is a path length.
No. It's basically just it does this mapping. Like after mapping, you have to see the distance between Obama president plus distance between speaks and greets plus distance between media and press plus distance between Illinois and Chicago.
Okay, thank you.
So there is one question. What is that ambiguity? Madam, in pictorial summarization, if the description of the figure has some external textual ambiguity, then will that affect deeply? Yes, that is always there. Yes, you are very correct. So like if the because we are relying that there is no ambiguity at all. Like the picture is described in text. That is our assumption. That the picture is not ambiguous in nature. Picture is thoroughly described in text. So our target is to extract those important sentences from the text to generate the summary for the particular figure. But if the figure is very ambiguous in nature and there are different possible descriptions possible, in that case, it's very difficult. And that aspect we have not considered. We have assumed that the picture is very straightforward pictures because we have considered the biomedical articles. The biomedical articles, in general, ambiguity is not there. These are basically results. The figures basically depict some experimental results. So that way, basically, some plots or some figures are there and the descriptions are available in the text. So we have only generated some important sentences from the text to generate the summary. But ambiguity part we have not tackled.
Okay.
which packages has been used to implement the optimization process. So optimization process, so you know the differential evolution, I think it is available in Python. Otherwise in C, C++ also the packages are available. Like in place of differential evolution or instead of differential evolution, you can also use the NSGA2. NSGA2 is also very popular multi-object optimization technique, which is called the non-terminated sorting genetic algorithm 2. So basically that can also be used. So I think Python, many packages are available. Apart from that, C, C+, I think in the next class I will show you Nobin, my PhD student who has basically done PhD on this particular topic on extracted document summarization. So he also has a web or GitHub page. So most of the my implementations are available in his GitHub page. How to apply code reference resolution that help in text summary? Yes, code reference resolution is also important because it basically helps in mapping the entities. So in order to understand that some entities refer to each other, code reference resolution is important because otherwise if suppose that the same entity is referred in different ways in a different document in a particular document, like Sriparna Shaha can be referred by Professor Shaha or Dr. Shaha or only Sriparna. So first, in order to understand that these are the mentions of the same entity, we have to apply code reference resolution. So by applying code reference resolution, we can easily understand that these are basically mentioning about the same entity. And then maybe we can easily group the sentences into a single sentence. So yes, so we have not applied because the data set was not like that. In the data set, code reference resolution was not required. But in real life, like in scientific document summarization, we're also working on the scientific document summarization. So in the scientific document summarization, we often, authors are often mention we, our. So, to resolve those things, I think code reference resolution is very much useful. Please share the PPT with all of us and in description notes for today's now. Okay. If you can, the implementation next session, yeah, we will show. Sure. Yeah. So Jyotirmoyi, why unsupervised technique is used here? So as I mentioned, that this DUC 2001 and DUC 2002 are having actual goal summary available. That is very much true. But if you want to train a neural network based approach, you need a huge corpus. Like you need to have the original document and also the corresponding summary. But that is not the that is not available. So such a big corpus is not available online. So supervised techniques are not very popularly, because supervised techniques require huge corpus for training, and for summarization problem statement it is very difficult to develop. That's why supervised techniques are not very popular, and we are basically using the unsupervised techniques. But yes, there are many unsupervised techniques available. Especially Google is having a large collection of data, so they are building their own summarization systems.
Madam?
Yes, tell me.
Yes, madam, thank you. I got it. Madam, another one question I have, for extractive summarization, we have so many methods, like machine learning method, text rank algorithm, deep learning method, so many methods are there. So why you have choose multi-objective optimization? Means is it giving more accuracy or what? That actually my research area is also on text summarization. That's why I'm asking. So on which field I should go ahead?
Yeah, so basically you can see our results. So we are able to achieve, we are able to outperform this Lex rank, text rank. Okay. So our results, the root score values for these two benchmark data sets, we are able to outperform the existing techniques. So basically our motivation was to simultaneously optimize, because we have seen that for summarization, multiple objectives are very much required. Like You have to improve the diversity. Also, you have to reduce the anti-redundancy. So there are many conflicting objective functions. So that is the motivation of using the multi-object optimization concept here, because there are many conflicting objective functions. So you can easily, if you are doing research, you can pursue using multi-object optimization concepts. Also, maybe you can think of making applications of summarization. Like you can think of working in the scientific summarization field. Like scientific summarization is a very new research area. Like you can think of developing a tool for automatic literature survey writing. Or we are facing difficulty in how to automatically writing literature survey. So if you can develop a tool based on the summarization systems for automatically writing the literature survey, maybe that will be a very interesting research area. Or maybe you can also investigate more into multimodal summarization. So like maybe in the next class I will show you, like I mentioned about this tweet summarization. So tweets during the tweet tweet users often upload images as well. So can we use images and text together for generating summary? So basically you can see the newspapers when they are now reporting the news, they are also showing some images. These images are very important because sometimes a image conveys more information than text. So image is equivalent to 1000 words. So like there is a statement like that. So can we utilize the image information as well as the text information both to generate a summary? So this is called the multimodal summarization. And image could be of supplementary nature or it could be of complementary nature. So like what is present in the text, maybe some additional information is present in the image, then that is called the complementary. But if the what is present in the text image also contains the same information, then this is called a supplementary. So maybe you can think of all these aspects.
Madam, can
Is
we
it for
employ
web
one
page or-
optimization technique with another optimization like particle?
Hello?
Hello, ma'am, am I audible?
Yeah, you're audible now. Yes.
Ma'am, I'm asking that suppose I am using particle swarm optimization, with that another optimization technique to summarize it, or it can be used, can be done.
Yeah, hybrid. There are many hybrid optimization techniques available. So people are nowadays also working on the hybrid optimization techniques. So you can also develop your own hybrid optimization techniques. Like you can combine some operators of differential evolution with some operators of genetic algorithm. So like that, you can also develop some hybrid optimization techniques.
Okay. And madam, for that different types of summarization, the data sets should be different, no? And how can we get those data set? Like for
Which one?
figurative summarization.
For
For
figurative, I have shown the link. Now you can, from that link, you can download the datasets freely.
Yes, madam. Like that, for other summarization techniques, what are the data sets available? How can we get that? I'm asking.
So
For
you
microbiology.
please visit my web page. So we are working in the microblog summarization. I have some publications related to microblog summarization as well. So there we have mentioned about the link from where we got the data set.
Okay, ma'am. Thank you.
Yeah, so
Okay, madam.
Prakash, so to figure out some information from the image, we have used different deep learning techniques. Like VGG19, ResNet, these are some deep learning packages for image processing. These are basically huge deep learning packages based on the CNN, and those are trained on large corpus like ImageNet. So we have used those deep learning tools on the images to extract the features.
Ma'am, I have a question.
Yeah, please tell.
Ma'am, again, I will. My question is again about multimodal. The thing is that I'm working on speech. So the word mover distance that you have mentioned here, it is working using word to vec, like word embeddings. what is there any method where we can combine the acoustic and word embedding method, and will this method be helpful for that case?
See, we have not combined, like when we develop the multimodal summarization, no, that time also, like first, what you have to understand is that, embeddings are having different vector spaces, like what to vec is having his own vector space, and suppose you are using the Open Smile or some VGGIS. So these are the tools available for extracting audio features, okay? So this VGGIS is a deep learning based tool where you can give the audio signal and you can extract some features. Or you can use the Open Smile, which is also a tool for extracting features from the audio signals. But the vector spaces are different. So first, you have to align the vector spaces. The vector space of the text and the vector space of the audio should be aligned together. And then only you can somehow compare them using this word mover distance.
Okay. Thank you so much, ma'am.
Yeah, I think now we should stop because already it is 8:21. So yes, so I will have two more lectures in this in this workshop. So yeah, I will be discussing about the dialogue systems and also a demo on summarization. There we will show you some approaches which are available for summarization, and also I will discuss about this multimodal summarization in detail. Yeah,
Is it okay? Can I ask one last question?
Yeah, please go ahead. Yes.
Yeah, my question is like one last question, no?
Yeah, sure, no issue.
Huh? Sure. Yeah, suppose if I have an image, okay, and you are talking about multimodal summarization, right?
Yes.
Multimodal document summarization where you take image and text is there, okay?
Yeah.
And now I have summarized the text, okay? So I have some summarization content. So I want to find a similarity between image and the summarized text, okay? Because you may have a lot of images in that. Out of those images, there might be one particular image which might having a close reality with the summarized output. So, like, how can we do it? Like, the vector model will work, or like, what is the thing that is going to?
Yeah, so as I mentioned that you have to use the VGGNet or VGG19 or the ResNet to extract the image vector.
Yes, that we can do. Even though we can take CNN or whatever may be the case, we are going to just take that one last layer of that one, okay, before one layer, and we will get the vector space. Vectors we will get it from the image. That's not a big deal. But now, how you are going to compare the similarity between?
No. So you cannot directly compare. You have to first align them together. So there are different tools. So there are some tools available which basically align these two spaces. So we have a text vector space and we have an image vector space.
Yes.
So some mapping is required.
Yes. That was my question. How is there anything? Yeah.
So there is a paper. Okay, we have used a tool which is available in a paper. So can you please? Please.
If possible, can you share that in the chat window or something?
Yes. I'm just typing that. I think I have that in the slide. My slides are visible. Still, it is visible. No, na?
No.
Okay. Let me share it. Okay, actually, that was I decided to discuss that, but yeah. This is our multimodal summarization. Yeah. This paper, can you see? Learning deep structure preserving image text embedding by Wang et al.
Okay.
It is in CVPR 2016. So this paper is having a, by using this approach, we have mapped the text embeddings into the same space of the image embeddings.
Okay.
So we are generating the text feature vectors, we are generating the image feature vectors, and then by following this methodology, we are mapping them into the same space. Then only we are comparing them together.
Okay. Thank you, ma'am. Thank you very much for your input. Thank you, Dr. Bhaskar, and sorry for others.
No, it's okay.
Thank you, madam. It was a really nice session. You can see in the chat box, the students, participants are giving nice feedbacks. There are lots of questions from which we can understand that the people who was engaged throughout the session.
Thanks,
So
my
thank you
pleasure.
again,
Yes.
madam.
Yeah,
And
thank you.
good
So
night,
we'll see you.
everybody.
Yeah, good night.
Please, ma'am.
It's already 8:25. Yeah. Thank you. Bye. See you.
Okay, then good night. I'm ending the meeting.
Hello, Bhaskar sir.